When people first hear that the Milky Way is big, the word rarely carries its true meaning. Human intuition evolved for kilometers, not kiloparsecs. Even modern space missions that travel billions of kilometers barely scratch the surface of what a galaxy actually is. The Milky Way is not a loose collection of stars spread thinly through space. It is a gravitational structure roughly 100,000 to 120,000 light-years across, with a disk about 1,000 light-years thick in its central region and flaring to several thousand light-years toward the edges. That means light itself, moving at the fastest speed anything can move, takes over 100 millennia just to cross it. Imagine a journey across a galaxy so vast that even light takes 100,000 years to cross it. No matter how advanced a civilization becomes, the Milky Way is a home you can explore but never truly leave. If you're fascinated by the mysteries of distant worlds and the search for life beyond Earth, subscribe now and let's start our journey. Astronomers estimate that the Milky Way contains between 100 and 400 billion stars. Even the lower estimate already overwhelms comprehension. The nearest star to the Sun, Proxima Centauri, is about 4.24 light-years away. If the Sun were reduced to the size of a grain of sand, Proxima Centauri would be another grain several kilometers away. That distance is considered nearby in galactic terms. Most stars in the Milky Way are separated by several light-years, and large regions of the galaxy contain vast voids with almost nothing in between. This spacing alone destroys the idea of a galaxy as a place one can simply cross with advanced vehicles. The Sun itself orbits the galactic center at a distance of about 26,000 light-years, completing one orbit roughly every 225 to 250 million years. This motion, known as a galactic year, already hints at the timescales involved. Dinosaurs lived and went extinct before the Sun completed even half of one galactic orbit. Human civilization, by comparison, occupies less than 1/1,000,000th of that time. One of the most common misconceptions comes from visual representations. Photographs of galaxies compress unimaginable distances into a flat image. Spiral arms appear close together, glowing with dense clusters of stars. In reality, those arms are separated by thousands of light-years, and the stars within them are not tightly packed. If you could stand near one star in a spiral arm, most of the galaxy would be invisible to the naked eye. The night sky from any given location inside the Milky Way shows only a tiny fraction of its total structure. Early science fiction writers in the mid-20th century imagined galactic travel as an extension of interplanetary exploration. At the time, the full scale of galaxies was not yet measured with precision. Edwin Hubble's work in the 1920s established that galaxies were separate island universes, but the implications of their size took decades to sink in. Even today, many people subconsciously think of a galaxy as something one might traverse in a lifetime with the right engine. The numbers tell a very different story. Consider Voyager 1, the fastest human-made object ever to leave the solar system. Launched in 1977, it travels at about 17 kilometers per second relative to the Sunday. After more than 45 years, it has covered roughly 0.002 light-years. At that speed, reaching Proxima Centauri would take over 70,000 years. Crossing the Milky Way from edge to edge would take more than 6 billion years, longer than the time-complex life has existed on Earth. Even if propulsion speeds were increased dramatically, the galaxy remains vast. At 10% the speed of light, far beyond anything humanity can currently engineer, crossing the Milky Way would still require around 1 million years. That assumes a straight path through empty space, something the galaxy does not provide. The Milky Way is a rotating, dynamic system filled with moving stars, gas clouds, radiation fields, and gravitational disturbances. The mass of the Milky Way compounds the problem. Including its dark matter halo, the galaxy has a mass estimated at around 1 to 1.5 trillion times that of the Sunday. This mass creates a deep gravitational well extending far beyond the visible disk. The halo itself stretches out to at least 300,000 light-years, possibly more. Even if a civilization could reach the edge of the luminous stars, it would still be deep inside the galaxy's gravitational influence. Leaving the galaxy is not like leaving a planet or even a star system. It means escaping a structure whose gravity dominates an enormous volume of space. The idea of a clear boundary is misleading. Galaxies fade gradually, not abruptly. Star density decreases, gas thins, and then dark matter dominates. There is no wall to cross, no obvious marker that says outside the galaxy. Instead, any traveller must climb a gravitational gradient that weakens slowly over hundreds of thousands of light-years. This alone multiplies travel distances far beyond the already staggering size of the visible disk. Another overlooked factor is how little of the galaxy is usable for transit. Dense regions near the galactic center contain intense radiation, frequent supernovae, and strong tidal forces. The central bulge, about 10,000 light-years across, is crowded with stars orbiting rapidly around the supermassive black hole Sagittarius A star, which has a mass of about 4 million suns. Passing through or near this region safely would be an enormous challenge. As a result, most hypothetical routes would need to skirt around the center, adding tens of thousands of light-years to any journey. Even the Sun's location, relatively calm by galactic standards, is not static. Over millions of years, stars drift, spiral arms shift, and gravitational resonances alter orbits. A route plotted today would change over the timescales required to cross the galaxy. Navigation itself becomes increasingly complex as stellar positions evolve. Modern astronomical surveys reinforce this reality. The Gaia mission, launched by the European Space Agency, has mapped the positions and motions of over 1 billion stars with unprecedented precision. Its data reveal a Milky Way that is warped, rippled, and constantly evolving. Stellar streams from past galactic mergers stretch across tens of thousands of light-years. These structures show that even natural objects bound by gravity take billions of years to redistribute themselves within a galaxy. Expecting an engineered object to do better ignores what the data already tell us. When people imagine civilizations leaving their galaxies, they often picture dramatic technological leaps. Technology, however, does not change distance. It can only increase speed within physical limits. The scale of the galaxy remains unchanged, regardless of engineering capability. Understanding the scale of the Milky Way reframes many later discussions. The galaxy is not a simple backdrop for activity, but a structure whose dimensions vastly exceed biological and historical timescales. Any discussion of movement beyond it must first account for its size and the distances involved. The speed limit of reality. Once the scale of a galaxy is properly understood, a second barrier immediately comes into focus. Distance alone is not the only problem. The rate at which anything can move through space is tightly constrained by the underlying rules of physics. No engine, no material, and no intelligence can bypass this constraint. The universe enforces a speed limit, and that limit reshapes every idea of galactic escape long before technology enters the discussion. The fastest speed permitted for information, energy, or matter is the speed of light in a vacuum, approximately 299,000 792 kilometers per second. This value is not arbitrary. It emerges from the structure of space-time itself and has been confirmed through countless experiments over more than a century. Particle accelerators such as CERN's Large Hadron Collider routinely push protons to more than 99.999999% of light speed. Yet even with energies rivaling those found in the cores of supernovae, the particles never cross that threshold. This is not due to engineering shortcomings. It is a fundamental physical limit. The closer an object with mass gets to light speed, the more energy is required to increase its velocity even by tiny increments. The amount of energy rises exponentially, making near-light travel for macroscopic objects an entirely different scale problem than moving subatomic particles. This limitation becomes catastrophic when applied to spaceships. Accelerating a spacecraft with a mass even as small as 1,000 tons to 1/10 the speed of light would require energy on the order of the Sun's total output for several years. Sustaining that speed over interstellar distances multiplies the problem. Every stage of acceleration, deceleration, and course adjustment demands colossal energy and infrastructure. Even the most optimistic futuristic designs, such as nuclear pulse propulsion or antimatter engines, encounter the same constraints. The amount of fuel, storage requirements, and shielding against extreme radiation from high-velocity collisions make such journeys increasingly unrealistic. Relativistic effects also come into play. As velocity increases, time dilation becomes significant. Clocks aboard fast-moving spacecraft tick more slowly compared to those at rest, a phenomenon predicted by Einstein's theory of special relativity and repeatedly verified through experiments using atomic clocks on aircraft and satellites. GPS satellites, for instance, must constantly correct for time dilation caused by both their speed and the gravitational field of Earth to maintain accuracy. For spacecraft travelling at a substantial fraction of light speed, these effects become pronounced. Messages sent across interstellar distances would take correspondingly long times to arrive. Moreover, time dilation does not reduce the total energy required. Even if passengers age more slowly, the spacecraft still needs to overcome immense inertia and shield itself from relativistic hazards. At high speeds, even the sparse gas of interstellar space becomes dangerous. Hydrogen atoms, cosmic dust, and stray particles collide with the craft, with energies capable of penetrating armor and generating intense radiation. At 10% of light speed, a collision with a single hydrogen atom releases kinetic energy comparable to a small atomic explosion on a microscopic scale. Multiply this by the billions of collisions over a multi-light-year journey, and shielding alone requires extensive engineering. Observational astronomy underscores the universality of the speed limit. No naturally occurring object with mass has ever been observed travelling at or above the speed of light. Even cosmic phenomena that appear superluminal, such as relativistic jets emitted by quasars or active galactic nuclei, are illusions of projection. Detailed measurements confirm their velocities remain below the universal limit. The highest measured speeds for massive objects in these jets approach 0.99 times the speed of light. But even this does not allow practical travel across galactic scales. The laws of physics remain consistent across the universe. Attempts to circumvent these constraints often involve speculative physics. Warp drives, wormholes, and Alcubierre bubbles are discussed frequently in theoretical literature. Yet, all known proposals rely on exotic matter or negative energy densities that have never been observed in quantities sufficient to be practical. Experiments searching for violations of special relativity, Lorentz invariance, or the speed of light limit, have repeatedly returned null results. Observations of gamma-ray bursts, neutrino flux, and cosmic microwave background radiation confirm that these limits apply everywhere. If a loophole existed at usable scales, evidence would have appeared in the data collected over decades by facilities such as the Fermi Gamma Ray Space Telescope or IceCube Neutrino Observatory. Real-world examples of human engineering reinforce the scale problem. Voyager 1, launched in 1977, moves at about 17 kilometers per second relative to the Sunday. After more than 4 decades, it has covered only 0.002 light-years. Even New Horizons, which flew past Pluto and continued outward at roughly 16 kilometers per second, would take tens of thousands of years to reach the nearest stars. The Parker Solar Probe, currently the fastest human-made object relative to the Sun, achieves speeds up to 190 kilometers per second at perihelion using solar gravity assists. Even at this record-breaking speed, it would take over 6,500 years just to reach Proxima Centauri, and millions of years to cross the galaxy. These examples are not hypothetical. They are the cutting edge of current engineering and reveal the sheer mismatch between velocity achievable with matter and the distances separating stars and galaxies. Momentum conservation presents another formidable hurdle. Every method of propulsion relies on either expelling reaction mass or interacting with an external medium. Rockets must carry fuel, which adds weight and decreases efficiency. Concepts like light sails eliminate onboard fuel but require perfectly aligned and uninterrupted energy beams over light years. Misalignment or beam dispersion over such distances would render navigation impossible. Even theoretical beam-powered propulsion scales poorly. The required laser arrays would need to output energy equivalent to billions of suns continuously, and any failure in maintenance would doom the mission. Environmental effects also compound the problem. High-speed travel through interstellar space exposes spacecraft to cosmic rays, micrometeoroids, and electromagnetic fields. At relativistic speeds, even the tiniest interstellar particle behaves as a miniature missile. Engineering materials capable of surviving collisions at such energies do not exist, and speculative proposals often underestimate both the cumulative radiation dose and the structural stresses over multi-million-year journeys. Biological life would experience catastrophic exposure, and even advanced robotic systems would require near-constant self-repair capabilities far beyond any known technology. Even cosmic expansion becomes relevant for extreme trajectories. On scales beyond galactic clusters, the universe itself stretches space, increasing separation between objects. While negligible inside a galaxy, this expansion slightly modifies trajectories over intergalactic distances. For spacecraft attempting to leave not just a galaxy but an entire cluster, maintaining speed relative to an expanding spacetime would require continuous energy input. This effect magnifies the already staggering challenges of propulsion, energy supply, and shielding. Finally, the absence of evidence for intergalactic travelers aligns with observations. Astronomical surveys have found no detectable high-energy propulsion signatures or anomalous radiation patterns that would indicate civilizations moving at relativistic speeds through the galaxy. High-speed travel would generate observable emissions in gamma rays, X-rays, and neutrinos. Yet extensive data from observatories such as Chandra, Fermi, and IceCube show no such signals. The combination of relativistic physics, energy demands, particle hazards, and time dilation makes motion at galactic scales vastly more challenging than travel within a star system. Even near light-speed travel requires unprecedented energy, shielding, and coordination over extremely long durations. The speed of light represents a physical limit for travel and information transmission. All known objects with mass are constrained by this limit, and any motion approaching it requires exponentially increasing energy and shielding considerations. Energy economics of intergalactic escape. Even if a civilization could approach the speed of light, another, more unforgiving barrier emerges: energy. Motion on planetary scales is expensive, but motion on galactic scales is catastrophically so. The numbers involved are no longer matters of engineering ingenuity. They are astronomical truths dictated by mass, velocity, and the physics of energy. Understanding why energy alone prevents civilizations from leaving a galaxy requires examining the requirements in precise, quantitative terms. A small starship, just a few thousand tons, might seem manageable. For comparison, the International Space Station weighs about 420 metric tons, and Voyager 1 is just 0.8 metric tons. Yet even scaling up to a modest interstellar vessel, the energy required to reach relativistic velocities becomes comparable to the output of entire stars. The Sun emits approximately 3.8 times 10 to the power of 26 watts continuously. To accelerate a vessel with the mass of a small city to 10% of light speed would require energy on the order of 10 to the power of 22 megajoules. That is equivalent to hundreds of millions of years of the Sun's total energy output, assuming perfect efficiency, something no real system could achieve. This calculation highlights a fundamental problem. Energy is not just needed to accelerate; deceleration, course corrections, and shielding against collisions all demand additional input. For multi-million-year journeys, even tiny inefficiencies compound into large totals. Fusion-based propulsion, long considered one of the most promising near-future concepts, is limited by fuel availability and energy density. Deuterium-tritium fusion produces roughly 17.6 MeV per reaction. To accelerate a single metric ton to relativistic speeds, trillions of such reactions would be necessary, requiring extremely large quantities of fuel. Historical experiments underscore how steep these challenges are. Project Orion in the 1960s explored nuclear pulse propulsion, theoretically capable of launching massive payloads. Calculations suggested a 4,000-ton spacecraft could reach several percent of light speed using thousands of small nuclear explosions as propulsion events. Yet the design required launching hundreds of nuclear devices, precise detonation timing, and a platform capable of surviving repeated near-nuclear shocks. Scaling this approach to higher velocities increases both the number of devices and the energy required exponentially, and even modest errors would destroy the craft. The sheer magnitude of resources, materials, and precision makes these concepts largely symbolic at galactic scales. Antimatter engines, a popular theoretical idea, provide even more extreme examples. Antimatter reactions convert nearly 100% of mass into energy, compared to less than 1% in chemical fuels. 1 gram of antimatter reacting with 1 gram of matter produces roughly 1.8 times 10 to the power of 14 joules, equivalent to the energy released by 43 kilotons of TNT. That sounds promising until the scale of galactic travel is considered. Propelling a 10,000-ton ship to 1/10 the speed of light would require thousands of tons of antimatter. For reference, the entire production of antimatter on Earth since the 20th century is less than a nanogram. Creating, storing, and safely handling the required amounts is beyond the scope of any feasible technology. Even ignoring fuel, mass, energy demands extend to environmental interactions. A ship traveling at relativistic speeds collides with interstellar gas and dust, converting motion into intense radiation. Shielding against these effects is not optional. At 0.5 times the speed of light, even sparse hydrogen atoms can generate energetic showers capable of vaporizing unprotected materials. The energy required to maintain structural integrity, protect life support systems, and power computational guidance is enormous. In essence, acceleration energy must be multiplied by an order of magnitude to sustain survivable conditions. Large-scale energy collection methods have been proposed to address these challenges. Dyson spheres, a theoretical megastructure surrounding a star to capture most of its energy, could theoretically provide the required power for Starship propulsion. A Dyson sphere around the Sun could yield roughly 3.8 times 10 to the power of 26 watts continuously, enough to fuel immense projects. However, even building a Dyson sphere introduces logistical challenges. The total mass of Earth alone would not suffice to construct one, and material collection would require dismantling entire planets or asteroid belts. Energy remains available in theory, but not practically accessible. Cosmic infrastructure imposes additional constraints. Even if a civilization could harness multiple stars' energy, the efficiency of transmitting that power into propulsion is limited. Laser-pushed light sails offer one possible method, but diffraction, misalignment, and absorption losses reduce efficiency dramatically over light years. For instance, a sail intended to accelerate a 1,000-ton vessel to zero, 1c over 10 light years, would require a laser array outputting energy comparable to that of thousands of suns, sustained for decades. This is not a theoretical curiosity. It demonstrates that energy, even if technically available, cannot be concentrated or applied with sufficient precision on galactic scales. The problem of energy also ties directly to the mass of the galaxy itself. The Milky Way contains roughly 1 trillion solar masses, including stars, gas, dust, and dark matter. Any attempt to leave the galaxy entails climbing out of this gravitational well, which, while weaker than a planetary field, extends over hundreds of thousands of light years. Escaping a gravitational well of this magnitude requires additional kinetic energy proportional to the potential energy of the system. Even ignoring drag from interstellar matter, the energy budget increases dramatically simply to move from the inner disk to the outskirts. Historical perspective reinforces the mismatch between aspiration and reality. Humanity's first chemical rockets reached escape velocity from Earth at 11.2 kilometers per second. Over the next century, this was scaled to reach interplanetary velocities of tens of kilometers per second. By contrast, interstellar or intergalactic speeds require thousands or millions of kilometers per second. Attempts to extrapolate current propulsion technologies linearly fail when faced with the exponential growth in energy required. Even speculative ideas, such as black hole-powered engines, encounter practical limits. Rotating black holes could theoretically be tapped via the Penrose process or Hawking radiation to produce energy densities orders of magnitude greater than any fusion system. Yet the engineering challenge of creating, stabilizing, and safely harnessing such objects is beyond comprehension. Maintaining a spacecraft in proximity to a stellar-mass black hole for continuous acceleration introduces tidal forces, radiation hazards, and orbital instabilities that multiply energy demands yet again. Energy constraints also interact with human and biological considerations. Life support systems for multi-generational crews require constant power, radiation shielding, artificial gravity, and closed-loop ecological systems cannot be turned off for energy savings. The ship becomes a floating ecosystem whose energy needs scale with both mass and time. For robotic crews, computational systems face similar issues. Data storage, processing, and self-repair all consume energy at rates that rise with mission, duration, and scale. The longer the journey, the more energy is consumed, just keeping the spacecraft operational. Interstellar precedent offers insight into the scale of the problem. Stars convert mass into energy at immense rates. For example, a single solar mass star emits roughly 3.8 times 10 to the power of 26 watts, translating to more energy in a second than humanity consumes in millions of years. Attempting to harness even a fraction of that energy for propulsion requires structures on scales comparable to the star itself. Multiplying this requirement for ships capable of crossing galactic distances renders the challenge orders of magnitude beyond any conceivable engineering. Energy represents a physical constraint. Unlike speed, which is limited by relativity, or distance, which is finite, energy requirements scale rapidly with both mass and velocity. The combination of large distances, high velocities, and environmental interactions makes intergalactic travel extremely demanding. Calculations of intergalactic travel show that the energy required to accelerate, decelerate, shield, and maintain life support or computational systems greatly exceeds what current or foreseeable methods can provide. Even with megastructures, antimatter, or exotic engines, available energy is far below the amounts needed for galactic-scale journeys. The galactic radiation barrier. Even if a civilization could solve the problems of distance, speed, and energy, another obstacle emerges that cannot be engineered away through propulsion alone: radiation. Space is saturated with high-energy particles and electromagnetic events that become increasingly lethal as travel extends across galactic scales. Radiation is not a localized hazard but a pervasive environmental condition of the galaxy itself, varying by region and time and accumulating relentlessly over long journeys. Cosmic rays form the baseline of this problem. These particles, mostly protons, helium nuclei, and heavier ions, move at velocities approaching the speed of light and originate from supernova remnants, neutron stars, and active stellar regions. In interplanetary space near Earth, astronauts aboard the International Space Station receive about 80 to 160 millisieverts of radiation per year, several times higher than on Earth's surface. In interstellar space, beyond the protection of a star's heliosphere, radiation levels increase dramatically. Measurements from Voyager, one after it crossed the heliopause in 2012, showed that galactic cosmic ray intensity was roughly 4 times higher than inside the solar system. Radiation exposure has dose-dependent biological effects. For humans, acute radiation sickness occurs at doses above 1 sievert, while long-term cancer risk increases significantly above 100 millisieverts. A dose of 5 sieverts is often lethal without immediate medical intervention. Over journeys lasting tens of thousands or millions of years, cumulative exposure would greatly exceed known survivable levels. Radiation damage is cumulative and irreversible at the cellular level, breaking DNA strands and overwhelming repair mechanisms. Gamma-ray bursts represent a more catastrophic threat. These events, caused by collapsing massive stars or neutron star mergers, release more energy in seconds than the Sun will emit over its entire lifetime. A gamma-ray burst occurring within a few thousand light-years could sterilize large regions of a galaxy. Astronomical observations suggest that such events occur in the Milky Way roughly once every few 100,000 years. Over a multi-million-year journey, the probability of encountering lethal exposure from at least one such event becomes significant. Shielding against gamma radiation at this scale would require layers of dense material meters thick, dramatically increasing spacecraft mass. Background radiation also varies dramatically across the galaxy. The Milky Way's spiral arms are regions of active star formation, containing massive stars that emit intense ultraviolet radiation and frequently explode as supernovae. These regions are rich in cosmic rays and energetic particles. In contrast, the outer galactic disk and halo have lower radiation density but are still far from safe. Even the relatively calm region near the Sun is punctuated by periodic supernovae within a few hundred light-years, events that can significantly increase radiation flux for thousands of years. Radiation exposure does not only affect biological organisms. Digital systems and artificial intelligence are vulnerable in different ways. High-energy particles cause single-event upsets in electronics, flipping bits in memory and corrupting data. Modern spacecraft already experience this problem. Satellites in Earth orbit regularly suffer from radiation-induced glitches despite shielding and error correction systems. Over long durations, error rates increase as memory corruption accumulates, processors degrade, and sensors lose accuracy. Shielding presents its own set of problems. Effective radiation shielding requires mass, typically hydrogen-rich materials such as water or specialized polymers. For protection against galactic cosmic rays, studies suggest shielding equivalent to several meters of water thickness. For a spacecraft large enough to house ecosystems, this would translate into millions of tons of shielding mass. That mass must be accelerated, decelerated, and maintained structurally, feeding back into the energy problem already mentioned previously. Shielding against gamma rays is even more demanding, requiring dense materials such as lead or tungsten, which further increase mass and engineering complexity. Magnetic shielding has been proposed as an alternative. By generating powerful magnetic fields, a spacecraft could deflect charged particles in a manner similar to Earth's magnetosphere. However, cosmic rays include heavy ions traveling at relativistic speeds, which are difficult to deflect without magnetic fields far stronger than any currently achievable. Generating and sustaining such fields over millions of years would require continuous energy input and superconducting materials capable of surviving intense radiation themselves. No known material can maintain such performance indefinitely in a high radiation environment. Radiation damage also affects structural materials. High-energy particles displace atoms within metals and composites, causing embrittlement, swelling, and microfractures. Nuclear reactors on Earth experience this problem over decades, requiring frequent maintenance and component replacement. A starship exposed continuously to cosmic radiation would face structural degradation on timescales far shorter than its journey. Self-repair mechanisms would be required, but these in turn depend on energy, raw materials, and precise manufacturing capabilities that cannot be guaranteed in deep space. The distribution of radiation hazards across the galaxy further complicates travel planning. Dense regions near the galactic center contain higher concentrations of energetic particles, stronger magnetic turbulence, and more frequent supernova events. Sagittarius A star, the supermassive black hole at the Milky Way's core, is surrounded by a chaotic environment of intense X-ray and gamma radiation. While it is relatively quiet today, evidence suggests periodic flaring events that release enormous energy. Avoiding such regions would require longer routes, increasing exposure time, and cumulative radiation dose. Even regions considered quiet are not static. Over millions of years, stellar orbits shift, spiral arms rotate, and star-forming regions migrate. A path that avoids radiation hazards at one epoch may intersect dangerous regions later. Predicting radiation environments over galactic timescales exceeds current astrophysical modeling capabilities. Studies of extremophiles on Earth sometimes inspire optimism. Certain bacteria can survive radiation doses thousands of times higher than what would kill humans. However, survival is not the same as maintaining complex, functional ecosystems or advanced technological systems. Multicellular organisms, neural tissue, and delicate biochemical processes are far more vulnerable. Even digital systems require stable environments to preserve information integrity over long periods. Evidence from space missions reinforces these concerns. The Mars Science Laboratory measured radiation levels on the journey to Mars and on its surface, revealing that even a 6-month trip exposes astronauts to significant health risks. Scaling this exposure up by factors of thousands or millions results in cumulative doses far beyond known biological tolerance. Robotic missions fare better, but still face cumulative damage that limits operational lifespan. Radiation also interacts with energy systems. Solar panels degrade under constant particle bombardment. Nuclear reactors suffer from neutron embrittlement. Energy storage systems lose capacity and reliability. Over extended durations, the infrastructure needed just to survive the radiation environment becomes an ever-growing burden on the mission, demanding more mass, more energy, and more complexity. Radiation exposure is pervasive. Unlike propulsion or navigation, which can be optimized or rerouted, radiation is present throughout interstellar space. All trajectories accumulate dose over distance and time, affecting both biological organisms and machines. Furthermore, cosmic rays, gamma-ray bursts, background radiation, and material degradation interact with spacecraft systems. These factors increase mass requirements, energy consumption, maintenance demands, and uncertainty over long-duration travel. When considered alongside size, speed, and energy constraints, radiation represents an additional environmental factor affecting long-duration travel. The galaxy contains active astrophysical processes that generate persistent radiation fields over cosmic timescales. Navigation fails beyond the stellar neighborhood. After radiation, another less dramatic but equally decisive barrier emerges: navigation. Traveling through a galaxy is not simply a matter of pointing in a direction and accelerating. Accurate navigation depends on stable reference points, predictable motion, and the ability to correct errors over time. At galactic scales and over multi-million year durations, all three of these foundations collapse. The galaxy is not a static map. It is a shifting, rotating, and evolving system that undermines long-term navigation in ways no technology can fully overcome. Modern spacecraft navigation relies on surprisingly fragile assumptions. Missions such as Voyager, New Horizons, and Cassini used a combination of inertial guidance, star trackers, radio ranging, and Doppler shift measurements. Position and velocity were constantly updated using signals sent to and from Earth's deep space network, a system of radio antennas spread across the planet. Even with this support, navigation errors accumulate quickly. A tiny miscalculation during a gravity assist can send a spacecraft millions of kilometers off course. These errors are manageable only because mission durations are measured in years or decades, not millennia. Beyond the immediate stellar neighborhood, Earth-based navigation becomes useless. Radio signals weaken with distance, and two-way communication delays grow from hours to years and eventually to thousands of years. Autonomous navigation becomes mandatory. Proposed methods rely on pulsars, rapidly rotating neutron stars that emit highly regular pulses of radiation. X-ray pulsar navigation, or XNAV, has been tested experimentally, including on the sextant demonstration aboard the NICA instrument on the International Space Station in 2017. The results showed position accuracy on the order of several kilometers, an impressive achievement for near-Earth space. However, pulsar navigation has hard limits. Pulsars are not evenly distributed across the galaxy, and their apparent positions shift over time due to proper motion, gravitational interactions, and galactic rotation. Over thousands or millions of years, pulse timing, noise, glitches, and spin-down rates introduce uncertainties that grow steadily. Even tiny deviations compound into enormous positional errors when extrapolated over galactic distances. A navigation error of 1 arc-second translates into a positional uncertainty of more than 1 light-year after travelling 200,000 light-years. The galaxy itself is in constant motion. The Milky Way rotates at roughly 220 kilometers per second at the Sun's location, but this speed varies with distance from the galactic center. Stars follow differential orbits, meaning inner regions rotate faster than outer ones. Spiral arms are not fixed structures but density waves that drift relative to stars. Over the duration of a hypothetical galactic crossing, the destination itself will have moved tens of thousands of light years from its original position. Any trajectory planned in advance becomes obsolete long before arrival. Gravitational drift further destabilizes navigation. Every star, gas, cloud, and dark matter concentration exerts gravitational influence. Individually, these forces are weak, but over long durations they accumulate. A spacecraft traveling for millions of years would experience countless small perturbations that slowly alter its trajectory. Correcting these deviations requires continuous thrust and precise measurements, both of which depend on reliable reference frames that do not exist at galactic scales. Reference frames themselves degrade beyond the local arm. Near the Sun, astronomers use well-mapped stars with precisely measured parallaxes from missions like Gaia. Gaia has mapped over 1 billion stars with extraordinary precision, but even its catalogue has limits. Position accuracy decreases with distance, and proper motion uncertainties grow over time. After a few million years, even Gaia's data become obsolete. Stars change position, some explode as supernovae, others drift into obscuring dust clouds. The celestial landmarks used for navigation today will not exist in recognizable form on galactic travel timescales. Navigation also depends on knowing where you are relative to the galactic structure. The Milky Way's shape is not perfectly known. Dust obscures large portions of the disk, and estimates of spiral arm geometry, bar length, and halo extent continue to change as new data arrive. Even now, astronomers disagree on the exact number and shape of spiral arms. A civilization attempting to navigate across the galaxy would be relying on an incomplete and evolving map with uncertainties that grow rather than shrink over time. Error correction becomes mathematically unmanageable. In short-duration missions, small corrections can be made using limited fuel. Over galactic distances, correction opportunities multiply, but so does fuel consumption. Every course adjustment increases mass requirements and energy use, feeding back into the constraints already described. Eventually, the fuel required to correct accumulated navigational drift exceeds what the spacecraft can carry or generate. Time delay worsens the problem. Autonomous systems must make decisions without real-time feedback. A navigation error detected thousands of years after it occurs may be impossible to correct. The spacecraft may already be moving in a trajectory that diverges irreversibly from any intended path. Unlike planetary navigation, where gravitational wells provide opportunities for course correction. Interstellar and intergalactic space offers no such safety nets. The galactic environment also introduces dynamic hazards that interfere with navigation instruments. Radiation damages sensors, star trackers lose calibration, and optical systems degrade due to micrometeoroid impacts and atomic erosion. Atomic clocks, which support precise navigation, drift over time due to radiation exposure and component aging. Maintaining synchronization over very long durations requires continuous correction and replacement. Historical precedent reinforces this reality. Long-term human navigation systems, even on Earth, degrade rapidly without maintenance. GPS satellites require constant updates and replacements. Deep space probes experience sensor degradation within decades. No system built by humans has demonstrated reliable, autonomous operation for even a fraction of the time required to traverse a galaxy. Extending current reliability models by factors of 1 million exceeds reasonable engineering assumptions. Galactic navigation is also affected by unpredictable events. Passing near a rogue star, molecular cloud, or compact object can introduce sudden gravitational perturbations. The galaxy contains billions of such objects, many of them difficult to detect until relatively close. Avoidance requires detection at long range and rapid maneuvering, both of which are constrained by sensor range and available energy. Navigation failure does not require total system collapse. A deviation of even a few light years can result in missing an intended target entirely. Space at galactic scales is sparse, and encountering another nearby system is not guaranteed. Altering or halting a trajectory requires additional energy and reliable reference points. These issues apply equally to biological crews and artificial intelligence. Autonomous systems still rely on sensors, clocks, and models of the environment. AI does not bypass uncertainty. It must operate within it. Without external updates, even the most advanced system gradually diverges from reality as models drift from actual conditions. Over millions of years, this divergence becomes unavoidable. Navigation errors accumulate gradually. Small uncertainties arise from measurement limits, correction maneuvers, and environmental interactions that degrade instrumentation. Over extended durations, these uncertainties increase and reduce positional accuracy. The galaxy is a rotating and evolving system in which objects move relative to one another. Navigation is feasible at smaller spatial and temporal scales. At galactic scales, and over long durations, relative motion and changing reference points significantly reduce navigational precision. Over journeys lasting millions of years, changes in reference frames, environmental conditions, and system integrity alter the relevance of initial trajectories. Time itself becomes an enemy. Once navigation fails beyond the stellar neighborhood, a deeper problem asserts itself: time. Not time as measured by clocks or calendars, but time as a corrosive force acting on civilizations, systems, knowledge, and purpose. At galactic scales, travel durations stretch into millions of years, and at that point, time is no longer a neutral backdrop. It actively dismantles everything required for a journey to remain coherent. Crossing even a modest fraction of the Milky Way requires durations that exceed the lifespan of most stars in stable phases, let alone civilizations. At speeds that do not violate known physics, travel between opposite sides of the galaxy requires hundreds of thousands to millions of years. Even reaching the outer halo from the Sun's position takes on the order of 100,000 years. These timescales are not hypothetical projections. They are derived directly from observed stellar motions and achievable velocities. For comparison, anatomically modern humans have existed for roughly 300,000 years. Written language is barely 5,000 years old. Industrial civilization spans less than 3 centuries. No civilization currently known has demonstrated continuity over timescales comparable to those required for galactic travel. Empires on Earth collapse on timescales of centuries. Languages evolve beyond mutual intelligibility in less than 1,000 years. Technologies become obsolete within decades. Over tens of thousands of years, societies undergo significant transformation or fragmentation. Long-duration travel introduces generational turnover as a structural problem. A crew launched from an origin world would not be the crew that arrives. Their descendants would inherit a mission whose purpose may no longer be relevant or comprehensible. Sociological studies of isolated human populations show that belief systems, norms, and priorities drift rapidly even over a few generations. In a closed environment with no external contact, this drift accelerates. Over thousands of generations, the original mission becomes mythology rather than instruction. Technological drift compounds this problem. Maintenance of advanced systems requires not just spare parts, but knowledge. Complex technologies depend on industrial ecosystems, training pipelines, and cultural reinforcement. On Earth, even highly documented technologies have been lost when supporting institutions disappeared. Roman concrete, Greek fire, and early Chinese mechanical clocks vanished for centuries due to social collapse rather than lack of intelligence. Physical systems are not immune to time either. All engineered components experience wear, degradation, and failure. Bearings seize, seals degrade, materials fatigue, and microscopic defects grow. Reliability engineering uses failure rate curves that assume constant maintenance and replacement. Over millions of years, even components designed with extreme redundancy will fail. Self-repair systems introduce additional complexity and failure modes. Eventually, the maintenance infrastructure itself becomes the weakest link. Statistical modeling of long-duration missions illustrates these risks. Systems with a mean time between failure measured in tens of thousands of years are likely to experience failures over million-year spans. Redundancy delays failure but does not eliminate it. Each additional subsystem increases complexity and the number of potential failure points. Biology fares no better. Closed populations experience genetic drift, accumulation of deleterious mutations, and loss of diversity. Even with large starting populations, isolation over thousands of generations leads to inbreeding depression or divergence into forms adapted to the artificial environment rather than the destination. Studies of isolated animal populations on islands show measurable genetic degradation in as few as 100 generations. A million-year journey corresponds to tens of thousands of human generations. Attempts to mitigate this through cryogenic preservation or suspended animation introduce new problems. Long-term cryogenic storage of complex organisms has never been demonstrated beyond small samples and short durations. Radiation damage continues even in frozen tissue, slowly breaking molecular bonds. Over thousands of years, accumulated damage becomes lethal. Repairing this damage would require molecular-level reconstruction capabilities that remain speculative. Digital continuity faces analogous issues. Data storage media degrade over time. Magnetic domains lose alignment, solid-state memory suffers from charge leakage, and even optical storage is vulnerable to radiation and material decay. Error correction codes can compensate temporarily, but they rely on stable reference states and functional hardware. Over geological timescales, bit rot is unavoidable. Without continuous external verification, corrupted data becomes indistinguishable from correct information. Missions are defined by goals rooted in the context of their origin civilization. Over millions of years, political boundaries, scientific priorities, and environmental conditions change. Stars move, planets destabilize, and planetary systems evolve. A destination selected based on present conditions may undergo significant alteration over the duration of travel. The galaxy's own timescales exacerbate this. Spiral arms rotate relative to stars over tens of millions of years. Star formation regions ignite and fade. Supernovae reshape local environments. A destination chosen based on present conditions cannot be assumed to remain stable over the duration of travel. By the time a ship arrives, the environment it was designed for may no longer exist. Time dilation at high velocities, often suggested as a workaround, does not solve these problems. While travelers might experience less subjective time, the external universe continues aging. Infrastructure at the origin decays. Knowledge bases become outdated. Any attempt at coordination collapses. Arrival occurs in a future disconnected from the mission's origin, with no guarantee of compatibility or relevance. Even artificial intelligence systems are subject to temporal decay. Algorithms trained on initial data become misaligned as environments change. Long-term autonomous systems suffer from goal drift, where optimization criteria diverge from original intent due to cumulative adjustments. Without external calibration, even minor deviations amplify over time. This is not a philosophical concern, but an engineering one, observed in long-running software systems that evolve unpredictably. Historical analogues reinforce the danger of long timelines. Consider nuclear waste containment. Modern engineering struggles to design warning systems that remain intelligible for even 10,000 years. Languages change too rapidly. Symbols lose meaning. Institutions vanish. If preserving a warning message across a few millennia is nearly impossible, preserving a coherent mission across 1,000,000 years is vastly more so. Time also undermines accountability and correction. Mistakes made early in a journey may not manifest consequences until tens of thousands of years later. At that point, the original designers are long gone, and the institutional memory required to understand or fix the problem no longer exists. Feedback loops become so delayed that effective control collapses. The combined effect is gradual change rather than sudden failure. Over extended durations, accumulated divergence occurs in biology, technology, and social organization. Systems and populations adapt to local conditions over time. Over long durations, adaptive pressures influence system behavior and population structure. Local optimization becomes more prominent as conditions change over time. At galactic scales, time introduces constraints independent of propulsion, energy, or radiation. Long durations affect system integrity, information continuity, and coordination regardless of other factors. Over very long durations, increasing signal delays and internal change affect communication between distant systems. The communication blackout problem. As time stretches into tens of thousands and then millions of years, communication does not merely slow down, it breaks down entirely. The distances involved in galactic travel impose delays and distortions that transform communication from a useful tool into a fundamentally unreliable process. What begins as latency eventually becomes isolation, and isolation becomes permanent silence. Communication across space is constrained by the same speed limit that governs travel. No signal can propagate faster than light. Within the solar system, this creates manageable delays, about 8 minutes between Earth and the Sun, a few hours to the outer planets. Even at the scale of nearby stars, communication delays grow to years. Proxima Centauri, the closest star to the Sun, is over 4 light-years away, meaning a round-trip message exchange takes nearly 9 years. That delay alone eliminates real-time coordination. At galactic scales, the situation becomes far more severe. The Milky Way spans over 100,000 light-years. A message sent from one side to the other requires more time to arrive than the entire span of recorded human history. Communication between regions separated by 10,000 light-years involves delays exceeding known historical timescales, preventing interactive exchange. Signal degradation compounds the delay problem. Electromagnetic signals spread out as they travel, losing intensity with distance. To remain detectable across thousands of light-years, transmissions must be extraordinarily powerful. Modern radio telescopes, like the Arecibo Observatory, before its collapse, could detect signals comparable in strength to planetary radar emissions across several hundred light-years under ideal conditions. Beyond that range, signals rapidly fall below background noise unless power levels increase dramatically. Background noise is not trivial. The galaxy is filled with natural radio emissions from pulsars, quasars, ionized gas clouds, and stellar flares. At certain frequencies, the Milky Way itself glows brightly in radio waves. Any artificial signal must compete with this cosmic noise. As distance increases, distinguishing intentional communication from background radiation becomes increasingly difficult. Signals must be narrowband, precisely timed, and extraordinarily powerful to remain identifiable, driving energy requirements upward once again. Latency alone undermines coordination. Imagine sending instructions to a spacecraft traveling 20,000 light-years away. By the time the message arrives, the spacecraft's environment, trajectory, and internal state will have changed in unpredictable ways. Any corrective instruction is based on information that is tens of thousands of years out of date. Feedback loops collapse entirely. Control becomes impossible, not because of technological failure, but because causality itself imposes delay. Synchronization between sender and receiver also fails. Communication protocols rely on shared standards, language, symbols, timing conventions, and error correction methods. Over millennia, these standards drift. On Earth, languages evolve so rapidly that texts only 1,000 years old require translation. Over tens of thousands of years, even mathematical notation and units of measurement change. A message sent by one civilization may arrive to descendants who no longer interpret its structure correctly, even if the signal itself is intact. Power demands for sustained communication are high. Broadcasting a signal detectable across galactic distances requires energy comparable to that used by major industrial societies, sustained over long durations. Maintaining such transmissions would require energy infrastructure operating reliably over extended timescales. Directional targeting introduces additional complications. A narrow beam transmission conserves energy but requires precise aiming. Over thousands of years, both the sender and receiver move due to galactic rotation and local stellar motions. A beam aimed accurately today will miss its target entirely after a few thousand years unless continuously adjusted. Continuous adjustment requires up-to-date positional information, which itself cannot be obtained due to signal delay. This creates a paradox where accurate aiming depends on information that cannot arrive in time to be useful. Even if messages arrive, their content may no longer be meaningful. Instructions sent from an origin civilization assume shared context, goals, and priorities. Over long durations, the receiving civilization or spacecraft evolves independently. Decisions are made based on local conditions and survival pressures. Commands issued tens of thousands of years earlier may conflict with present realities, making them irrelevant or actively harmful. Communication loses authority and coherence. Evidence from astronomy reinforces the difficulty of detecting long-range signals. Decades-long searches for extraterrestrial intelligence have scanned large portions of the sky for artificial radio emissions. These surveys, conducted by projects such as SETI and Breakthrough Listen, have found no confirmed signals of technological origin. While absence of evidence is not proof of absence, it is consistent with the expectation that long-duration, high-power transmissions are energetically expensive and strategically unsustainable. Communication failures also affect internal coordination within a traveling civilization. Large spacecraft or distributed habitats separated by significant distances experience internal signal delays. Over time, these delays hinder unified decision-making. Subgroups develop independently, responding to local conditions rather than centralized plans. The larger and longer the mission, the more fragmented communication becomes, even without external distance. Digital communication systems degrade under radiation exposure and hardware aging. Error rates increase, and data packets may be lost or corrupted. Redundancy mitigates these effects temporarily, but long-term operation increases cumulative failure risk. The galaxy itself introduces communication hazards. Dense regions scatter and absorb radio waves. Ionized gas clouds distort signals. Gravitational lensing near massive objects can bend or amplify signals unpredictably. These effects introduce noise, delay, and distortion that vary with location and time. A transmission path that works at one epoch may fail at another due to changes in the intervening medium. Communication delay limits shared discovery. Scientific progress relies on feedback, replication, and correction. When delays exceed generational timescales, knowledge development becomes localized, and groups progress independently. Attempts to pre-program communication protocols for all future contingencies fail for similar reasons. No finite set of instructions can anticipate environmental, technological, and cultural changes over millions of years. Autonomous decision-making becomes mandatory, rendering external communication increasingly ceremonial rather than functional. Even theoretical concepts such as quantum communication offer no escape. While quantum entanglement enables correlations between particles, it does not allow faster-than-light information transfer. This limitation has been confirmed experimentally and is embedded in the foundations of quantum theory. Information still obeys the universal speed limit, leaving latency unchanged. Large spatial scales introduce increasing communication delays, energy requirements, and signal degradation. Coordination across galactic distances becomes increasingly constrained by distance and time. As communication becomes less reliable, navigation increasingly depends on local physical forces, including gravitational interactions within the galaxy. Galactic gravity is not a straight road. When communication collapses and navigation uncertainty grows, motion through the galaxy ceases to be a matter of intention and becomes increasingly dominated by gravity. Unlike the simplified trajectories often imagined in diagrams, the galaxy is not an empty backdrop where a spacecraft travels in a straight line. It is a massive, dynamic gravitational system in which every object is constantly being pulled, deflected, and reshaped by forces that accumulate over time. At galactic scales, gravity does not guide, it distorts. The Milky Way contains hundreds of billions of stars, vast clouds of gas and dust, dense star clusters, stellar remnants, and a dominant halo of dark matter. Together, these components create a complex gravitational field that varies with location and time. Even within the solar neighborhood, stellar motions are influenced by nearby stars, molecular clouds, and the galaxy's overall mass distribution. As distance increases, these influences multiply, turning long-distance travel into a problem of continuous perturbation rather than controlled motion. Most spacecraft trajectories today rely on relatively stable gravitational environments. Interplanetary missions exploit predictable orbits and gravity assists from planets whose masses and motions are well characterized. These maneuvers work because the solar system is dynamically stable on human timescales. The galaxy is not. Stars orbit the galactic center at different speeds depending on their distance, creating differential rotation. Over millions of years, this shears trajectories apart, even if they were initially aligned. A spacecraft traveling through the galactic disk is never free from gravitational influence. Passing stars exert small but persistent tugs. Individually negligible, these forces accumulate over long durations, gradually altering velocity and direction. This effect is similar to orbital diffusion observed in stars themselves. Astronomical studies show that stellar orbits change measurably over hundreds of millions of years due to repeated weak encounters. A spacecraft lacking the mass and inertia of a star would be even more susceptible. Gas clouds introduce additional complications. Giant molecular clouds can contain millions of solar masses packed into regions only a few hundred light-years across. Encounters with their gravitational fields can significantly deflect trajectories. These clouds are not static. They form, collapse, and disperse over tens of millions of years. A path calculated to avoid them at launch may intersect one later due to changes in both the cloud's position and the spacecraft's accumulated drift. The influence of dark matter further destabilizes long-range motion. Dark matter accounts for roughly 85% of the Milky Way's total mass and dominates its gravitational potential. While invisible, its distribution determines the rotation curve of the galaxy and affects the motion of all objects within it. Current models of dark matter halos are statistical, not precise maps. Small-scale clumps and density variations remain poorly understood. Over galactic distances, these unknowns translate into unpredictable gravitational perturbations. Tidal forces add another layer of difficulty. As a spacecraft moves through regions of varying gravitational strength, different parts of the structure experience slightly different accelerations. Over time, these tidal stresses strain materials, joints, and connections. In dense regions near star clusters or the galactic center, tidal forces can become significant, particularly over extended exposure. Designing structures that can tolerate continuous, low-level tidal stress for millions of years exceeds any existing engineering precedent. The idea of a clean escape vector from the galaxy also breaks down under gravitational scrutiny. To leave the Milky Way entirely, an object must overcome not just the gravity of individual stars, but the combined gravitational pull of the galactic disk, bulge, and halo. Even objects that appear to be moving outward are often still gravitationally bound, following long, looping trajectories rather than true escape paths. Observations of hypervelocity stars show that only a tiny fraction achieve speeds sufficient to escape the galaxy, usually after violent interactions near the galactic center involving the supermassive black hole. For engineered spacecraft, achieving and maintaining such trajectories is difficult. Any deviation reduces effective escape energy, potentially turning an intended exit into a bound orbit that curves back inward. Correcting this requires continuous thrust, which demands sustained energy and fuel over long timescales. Orbital instability outside the galactic disk introduces further challenges. The disk itself provides a relatively coherent plane of motion, but moving above or below it places a spacecraft into the halo where gravitational forces are less uniform and more influenced by dark matter distribution. Objects in the halo follow complex, three-dimensional orbits that are difficult to predict and harder to control. Minor perturbations can shift an object from a wide arc into a plunging trajectory back toward the disk. Gravitational interactions also interact with time and navigation failures. When positional uncertainty grows, it becomes harder to anticipate gravitational encounters. A misjudged approach to a star or dense region may lead to unintended acceleration or deceleration. Over time, these small errors compound, and the spacecraft's path diverges further from any planned route. Unlike in planetary systems, there are no well-defined orbits to stabilize motion or provide predictable correction opportunities. The galaxy's mass distribution is not static over long timescales. Star formation, supernova explosions, and galactic mergers continuously redistribute mass. The Milky Way is accreting smaller satellite galaxies, such as the Sagittarius dwarf galaxy, whose tidal debris stretches across the sky. These events alter local gravitational fields. Over millions of years, the cumulative effect reshapes orbital pathways throughout the galaxy. Even the Sun's own orbit is not fixed. It oscillates above and below the galactic plane roughly every 60 million years and drifts radially over time. A spacecraft launched from the solar system inherits this motion and enters a gravitational environment already in flux. Predicting how these inherited velocities interact with future galactic evolution introduces uncertainties that grow faster than correction capabilities. Attempts to counter gravitational drift with active stabilization encounter the same scaling problems seen in navigation and communication. Sensors must detect minute accelerations, actuators must apply precise corrections, and energy must be expended continuously. Over millions of years, sensor degradation, actuator wear, and energy limitations make perfect compensation impossible. The result is gradual loss of control rather than sudden failure. There is an asymmetry between gravitational influence and propulsion. Gravity acts continuously, while propulsion is intermittent and limited by available resources. Over long durations, continuous forces influence trajectories more strongly. Stars themselves experience orbital diffusion over cosmic timescales due to persistent gravitational interactions. Gravitational lensing and relativistic effects near massive objects further complicate trajectory prediction. Passing near neutron stars or black holes can bend paths dramatically. While such encounters are rare, their consequences are severe. Avoidance requires early detection and maneuvering, both constrained by limited sensing range and delayed response. Over extended durations, gravitational forces increasingly influence spacecraft trajectories. Initial trajectory control is progressively altered by the galaxy's mass distribution as corrective capabilities degrade over time. Galaxies impose strong gravitational constraints on motion. Objects embedded within their gravitational structure require significant energy to escape, and maintaining a specific trajectory over long durations is difficult due to persistent perturbations. Beyond the gravitational boundaries of the galaxy lies intergalactic space, which presents additional physical conditions distinct from those within the galactic environment. Intergalactic space is actively hostile. Leaving the gravitational structure of a galaxy does not deliver a traveler into a calm, neutral void. Intergalactic space is often imagined as empty and therefore safe, but this assumption collapses under closer examination. The regions between galaxies are environments defined by extremes: extreme cold, extreme isolation, and extreme vulnerability to even the smallest interactions. What makes intergalactic space dangerous is not what is present in abundance, but what is almost entirely absent. The most immediate condition is temperature. Intergalactic space sits only a few degrees above absolute zero, dominated by the cosmic microwave background at about 2.7 Kelvin. At such temperatures, conventional materials behave differently. Metals become brittle, lubricants freeze or evaporate, and chemical processes slow dramatically. Maintaining operational temperatures requires continuous energy input. Any lapse, even brief on human scales, allows systems to cool irreversibly, leading to cracking, warping, or complete failure of components. Cold alone would be manageable if energy were readily available. It is not. Intergalactic space contains virtually no usable energy sources. Stars are millions of light years apart. There is no ambient starlight to harvest, no dense gas to scoop, and no magnetic field strong enough for power generation. Once a spacecraft leaves its home galaxy, it becomes entirely dependent on energy it carries with it. Every watt of power must be planned for in advance, over durations that may exceed 1 million years. The scarcity of matter introduces another hazard: collisions at extreme velocities. Intergalactic space is not perfectly empty. It contains a thin distribution of hydrogen atoms, free electrons, and microscopic dust grains. The average density may be as low as 1 atom per cubic meter, but over millions of light years, even this sparse material becomes significant. At velocities of thousands of kilometers per second, impacts with individual atoms and dust particles release substantial energy relative to the mass of the spacecraft. Dust grains are particularly dangerous. A particle smaller than a grain of sand, when struck at relativistic speeds, carries kinetic energy comparable to an explosive charge. Studies conducted during the design of interstellar probe concepts, such as the Breakthrough Starshot Initiative, show that even millimeter-scale particles pose catastrophic risks at a fraction of light speed. In intergalactic space, where avoidance and detection are nearly impossible, cumulative impacts gradually erode shielding and structural surfaces. Unlike within a galaxy, there are no external resources available for repair. There are no nearby asteroids, gas clouds, or stars to supply raw materials. Micrometeoroid erosion gradually thins protective layers, exposes internal systems, and compromises pressure vessels over long durations. The absence of external resources eliminates redundancy strategies. A failed component cannot be replaced unless it was manufactured on board. Manufacturing requires feedstock, energy, and functioning machinery, all of which degrade over time, making self-sufficiency fully dependent on onboard reserves. Intergalactic radiation presents a different profile from galactic radiation, but remains hazardous. While cosmic ray density may be slightly lower outside galaxies, the lack of magnetic fields removes any natural shielding. Galactic magnetic fields help deflect charged particles, reducing exposure in certain regions. In intergalactic space, particles travel largely unimpeded. Over long durations, this steady exposure continues to damage materials, electronics, and biological tissue, compounding earlier radiation-related degradation without any mitigating environment. Thermal management becomes increasingly difficult. In near-stellar environments, excess heat can be radiated away efficiently against a warmer background. In intergalactic space, radiating heat into a near absolute zero background causes systems to lose thermal energy rapidly. Balancing internal heat generation against radiative loss requires precise control. Any imbalance leads either to freezing or overheating, both of which stress materials and electronics. Structural stresses also increase due to temperature gradients. A spacecraft exposed unevenly to internal heat sources experiences expansion and contraction across different regions. Over time, repeated thermal cycling causes fatigue fractures. On Earth, such effects are managed through maintenance and replacement. In intergalactic space, fatigue accumulates without relief. For biological crews, the absence of external reference points, no stars bright enough to form constellations, and no changing sky creates sensory deprivation. Studies from Antarctic winter stations and long-duration submarine missions show that isolation and monotony degrade cognitive function over months or years. Intergalactic travel extends these conditions over very long durations. For artificial systems, the absence of environmental variation reduces the effectiveness of sensors. Anomalies are harder to distinguish from background noise. Fault detection systems rely on comparative data that does not exist in intergalactic space, allowing undetected failures to accumulate. Another underestimated hazard is the lack of navigational anchors. Outside galaxies, gravitational reference points are weak and diffuse. A spacecraft cannot easily determine its position relative to any meaningful structure. Motion becomes inertial and largely unobservable. Without landmarks, even detecting unintended rotation or drift becomes difficult. Over long durations, this lack of feedback allows errors to persist unchecked. Intergalactic space also lacks time markers. Within galaxies, pulsars, variable stars, and orbital motions provide natural clocks. Outside, these signals fade into the background. Timekeeping becomes entirely internal, dependent on clocks that degrade over time due to radiation exposure and material aging. Loss of accurate timekeeping undermines navigation, communication, and system synchronization simultaneously. The scale of isolation amplifies every other problem. A spacecraft halfway between galaxies may be millions of light years from the nearest star. Any failure at that point is final. There is no possibility of rescue, assistance, or even detection. From an observational standpoint, such a spacecraft is effectively invisible. Its signals are too weak, its size too small, and its emissions too faint to be distinguished from background noise by distant observers. The low-density environment and great distances make intergalactic spacecraft effectively undetectable. Signals are extremely weak, objects are small, and emissions are faint, making detection by distant observers unlikely. Astronomical surveys have not identified confirmed intergalactic travelers. Intergalactic space is also not static over cosmic time. Large-scale structures such as galaxy filaments and voids evolve. Galaxies move relative to one another, pulled by mutual gravity. A target galaxy selected at launch will not remain stationary. Over millions of years, it may shift position by tens of thousands of light years. Without intermediate reference points, course correction becomes guesswork. These conditions produce continuous degradation of systems. Mechanical components wear, shielding erodes, energy stores decline, and accumulated errors persist. Intergalactic space lacks external resources or repair opportunities, so all failures must be managed with onboard reserves. These hazards do not depend on rare events. Continuous exposure to low temperatures, micrometeoroid impacts, energy scarcity, and radiation gradually damages systems over long durations. Intergalactic space is more hostile than galactic environments. Galaxies provide energy, material, gravitational references, and structural support. Outside galaxies, these supports are absent. Exiting a galaxy exposes a spacecraft or civilization to intergalactic conditions. Even after overcoming gravitational and energetic barriers, the environment provides no external energy, materials, or navigational aids. As systems degrade and onboard resources are depleted, continued operation depends entirely on internal reserves and system redundancy. Closed ecological systems must maintain stability over the extended durations required for intergalactic travel. The collapse of closed ecologies. The idea of carrying a self-contained ecosystem across interstellar distances is often portrayed as a solution to the challenges of long-term space travel. In theory, a closed ecological system could supply air, water, and food indefinitely, creating an artificial biosphere capable of sustaining a civilization while it navigates the vast expanses of the galaxy or even intergalactic voids. Reality, however, paints a much harsher picture. The longer such systems are maintained, the more fragile they become, and the longer the mission, the more likely ecological collapse becomes inevitable. Long-term experiments on Earth demonstrate the difficulty of maintaining stable closed ecosystems. Biosphere 2, the ambitious project constructed in Arizona in the early 1990s, was intended to operate as a fully sealed, self-sustaining habitat. It enclosed nearly 3.15 acres of rainforest, desert, and agricultural environments designed to support 8 humans for an indefinite period. Despite advanced planning and considerable engineering, the system experienced dramatic fluctuations in oxygen levels, crop failures, and microbial imbalances within just a few years. Controlled adjustments were required to prevent collapse, demonstrating that even with continuous human intervention, stability over decades was challenging. Smaller scale experiments provide similar lessons. The Russian BIOS 3 facility, operational in the 1970s and 1980s, demonstrated air and water recycling for human crews in a 315 cubic meter enclosure. Though technologically impressive, it required constant monitoring and manual adjustments. Microbial populations often shifted unpredictably, causing breakdowns in nutrient cycles and temporary loss of air quality. These experiments illustrate that even when the number of species and system complexity is limited, maintaining balance over long durations is extremely delicate. The primary challenge comes from the inherent unpredictability of biological evolution. Microbes and plants adapt continuously, sometimes in ways that destabilize their environment. In enclosed systems, mutations that would be negligible in a natural environment can have outsized effects. A single bacterial strain could evolve into a pathogen, a critical plant species could lose nutritional value, or algae populations could bloom uncontrollably, altering oxygen and carbon dioxide levels. Over centuries or millennia, these evolutionary dynamics are unavoidable. Closed ecosystems are also highly sensitive to minor fluctuations. Small losses of water, nutrients, or energy can cascade into larger failures. A leak of even a few litres in a multi-kilometre habitat would have negligible effects in an open environment, but could threaten survival in a sealed system. Temperature control becomes increasingly critical. Thermal cycling can affect plant growth rates, microbial activity, and water evaporation. The interdependence of system components creates a chain reaction. One subsystem failure often propagates to others. Nutrient cycling presents a particularly stubborn problem. In natural ecosystems, cycles of carbon, nitrogen, phosphorus, and other elements rely on vast networks of decomposers and interactions with soil, water, and atmosphere. In artificial systems, the closed loop must replicate these processes with limited biomass and limited redundancy. Studies of algal-based oxygen production in closed habitats show that even small imbalances in nitrogen or trace elements can reduce oxygen output and harm human occupants. Maintaining these cycles over millions of years, the timescales required for intergalactic travel is beyond any tested system. Microgravity and radiation further complicate matters. In long-duration spaceflight, experiments on the International Space Station have shown that plant roots grow differently, microbial activity changes, and water behaves unpredictably. Cosmic radiation alters DNA in microbes, plants, and potentially humans, introducing mutations that can disrupt system stability. Shielding can reduce, but not eliminate exposure, and heavy shielding increases mass, energy, and structural demands, creating a trade-off that worsens over time. Genetic bottlenecks are another hidden threat. Closed ecosystems often rely on a limited number of species and individuals. Over long durations, stochastic events or selective pressures can reduce genetic diversity, leading to extinction or loss of crucial traits. In animal populations, this can manifest in reduced fertility or increased susceptibility to disease. In plants, it can lead to crop failures. A self-contained habitat cannot easily introduce new genetic material, so the risk of collapse grows as populations evolve independently. Human factors compound these biological risks. Psychological stress, cognitive fatigue, and social strain are magnified in enclosed environments. Studies of Antarctic stations and submarine missions indicate that group dynamics, conflict resolution, and resource allocation become increasingly fragile over prolonged isolation. Even minor disagreements or mismanagement can escalate into system-wide crises when coupled with ecological fragility. Attempts to automate ecological management using artificial intelligence and robotics encounter additional challenges. While sensors can monitor oxygen levels, humidity, and nutrient concentrations, they cannot fully predict emergent biological behaviors. A robotic system might correct a short-term imbalance, but fail to anticipate longer-term trends caused by microbial evolution or plant adaptation. Hardware degradation over centuries further reduces reliability, creating a scenario where the very systems designed to maintain stability introduce new failure points. The problem of scaling is stark. Small, laboratory-scale ecosystems can sometimes remain functional for months or even years with careful intervention. Expanding to the scale needed to sustain thousands or millions of individuals multiplies the number of interacting components, increasing the potential points of failure exponentially. Space habitats designed for galactic travel would need redundancy not just for individual systems, but for entire ecological networks. No current engineering project has approached this scale in a controlled, stable manner. Resource limitations amplify these vulnerabilities. Closed habitats must generate food, water, and air internally. Energy must be constantly supplied, often from stored reserves or nuclear sources. Any interruption due to component failure, cosmic radiation, or micrometeoroid damage can lead to cascading failures in life support systems. Over thousands of years, the probability of uninterrupted operation trends towards zero. Intergalactic travel requires operation over extremely long durations. A journey to the edge of the Milky Way could take hundreds of thousands of years. Travel beyond may require millions. Current closed ecological systems have not been tested over such timescales. Cumulative effects from evolutionary changes, environmental perturbations, and material degradation can lead to operational failures over extended periods. Artificial life support systems, including hydroponic, algal, or chemically maintained atmospheres, are also affected by cumulative errors. Leaks, contamination, or miscalculations propagate through the system. Over extended durations, maintaining all subsystems continuously presents increasing technical and logistical challenges. Closed ecological systems face limits when operated independently of external resources. Galaxies provide energy, matter, and gravitational context that support life. Outside these environments, self-contained systems must rely entirely on internal resources, which deplete over long durations. Extended operation over thousands to millions of years increases the risk of system failure. Closed ecosystems demonstrate that sustaining life over interstellar or intergalactic durations requires reliable self-contained systems. Propulsion, navigation, and shielding alone are insufficient. Life support technologies must maintain air, water, and food over extended durations without external resources, which current systems have not achieved. Artificial intelligence doesn't solve the problem. When closed ecosystems prove fragile over millennia, many science fiction scenarios propose artificial intelligence as the ultimate solution. Autonomous machines, they argue, could maintain life support systems, navigate the galaxy, and even govern a civilization independently of human limitations. On paper, the concept seems elegant. Replace fragile biological continuity with durable, self-repairing, intelligent systems. In reality, the challenges multiply when examined on the timescales and distances required for galactic or intergalactic travel. One of the most immediate constraints is hardware degradation. All electronic systems, no matter how well designed, are subject to wear. Capacitors leak, solder joints fatigue, and semiconductor materials degrade over time. While spacecraft electronics can survive decades, Voyager 1 and 2 have been operational for over 40 years. These examples operate over human, not cosmic, timescales. Extending functionality over thousands or millions of years introduces cumulative failure probabilities that approach certainty. Even systems designed with redundancy, error correction, and radiation hardening cannot overcome fundamental material limits indefinitely. Cosmic radiation exacerbates these problems. Galactic cosmic rays and high-energy particles constantly strike any object outside protective magnetic fields. On Earth, the atmosphere absorbs most radiation, but in space, every bit of electronics is exposed. Modern spacecraft mitigate this with shielding, error-correcting memory, and hardened circuits. Despite these measures, high-energy particles cause bit flips, latch-ups, and component failure. Over long durations, even low rates of error accumulate, leading to data corruption and system malfunctions. For a spacecraft attempting to leave its galaxy, millions of years of exposure would likely overwhelm any protection scheme conceivable with known materials. Memory corruption is another limiting factor. Long-term autonomous systems rely on digital storage for navigation, system management, and decision-making. Even with error-correcting codes, permanent storage degrades. Studies in archival storage for space missions show that after decades, magnetic and solid-state media begin to fail. Extending this to a million-year voyage introduces errors that can corrupt operational algorithms, erode navigation tables, or disable life support control programs. Unlike biological systems, AI cannot adapt to physical data loss without pre-programmed resilience, which has practical limits. Self-repair mechanisms help, but cannot completely solve these problems. Proposals for self-replicating machines envision onboard manufacturing units that can fabricate new parts from raw materials. Yet these systems require supply chains, energy, and precision assembly capabilities. Intergalactic environments offer neither abundant raw materials nor stable energy sources. Even if a machine could fabricate components, it cannot indefinitely replace degraded systems without eventually exhausting available resources or introducing new errors. Small mistakes compound, leading to eventual systemic collapse. Goldrift presents a less obvious but equally severe challenge. Any AI system designed to manage a long-duration mission must operate under initially specified objectives. Over time, environmental conditions, unforeseen events, or internal errors can shift operational priorities. Experiments in long-running autonomous algorithms on Earth demonstrate that even minor deviations can propagate unpredictably. In an interstellar context, a spacecraft AI might prioritize resource conservation in ways that conflict with intended mission goals, or misinterpret sensor data due to radiation-induced corruption, producing unintended consequences that accumulate over centuries or millennia. Interfacing AI with biological life introduces additional complexities. Maintaining closed ecological systems, or human populations, requires fine-tuned decision-making that must respond to subtle variations in biological processes. AI can monitor oxygen levels, crop growth, and microbial populations, but emergent behaviors in biology often defy strict prediction. A mutation in a microbial population, unanticipated crop failure, or subtle environmental shift can cascade beyond programmed correction routines. Even sophisticated machine learning models struggle to adapt to completely novel conditions without retraining a process that cannot be performed in isolation without risk of failure. Energy management is another limiting factor. Every action an AI takes, computation, repair, propulsion, or environmental adjustment, requires energy. Over millions of years, energy reserves are finite, and replenishment is not guaranteed in intergalactic space. Even nuclear sources decay, solar arrays lose efficiency, and chemical fuels are exhausted. AI cannot invent energy. It can only manage what is available. Extended exposure to power shortages inevitably forces prioritization, which often sacrifices essential functions over time. The scale of complexity in long-duration, self-contained systems further compounds risk. Unlike short-term missions, galactic voyages require coordination among thousands of subsystems. Environmental control, structural integrity, propulsion, navigation, and communication. Each subsystem interacts with others, creating emergent behaviors that are hard to predict. Even small errors propagate through these networks, producing cascading failures. AI can mitigate, but it cannot eliminate the fundamental risk posed by scale, redundancy, and interdependence. AI also faces challenges imposed by uncertainty in the external environment. Navigation, collision avoidance, and resource utilization depend on accurate knowledge of surroundings. Pulsar navigation and gravitational modeling are imperfect over galactic scales. Dark matter distributions, uncharted stellar remnants, and interstellar dust introduce unknowns that cannot be fully accounted for in advance. Machine intelligence can model scenarios probabilistically, but the timescales involved ensure that models eventually diverge from reality, leaving AI to operate under progressively flawed assumptions. Even communication with origin civilizations becomes impractical. Galactic distances introduce latencies of tens of thousands of years. By the time a message arrives, the originating civilization may have evolved, collapsed, or disappeared. AI cannot rely on guidance or updates. It is forced into complete autonomy, further exposing it to the hazards of cumulative degradation, environmental uncertainty, and resource scarcity. AI-driven systems are affected by hardware degradation, memory corruption, and energy limitations, similar to closed ecological systems. Unlike terrestrial operations, interstellar missions offer no opportunity for resupply or external maintenance. Over long durations, cumulative small failures in components, software, and energy systems increase the likelihood of operational disruption. Historical attempts at long-duration autonomous systems on Earth illustrate these limitations. Satellite constellations, such as GPS and communication networks, require constant maintenance, monitoring, and replacement to function reliably. Despite rigorous engineering and abundant resources, system failures are inevitable within decades. Extrapolate these patterns over millions of years without external support, and failure becomes a near certainty. No AI can escape this statistical inevitability. Intelligence alone does not eliminate material and energy limitations. AI systems reorganize existing resources, and every maneuver, repair, or environmental adjustment consumes finite energy and materials. Over long durations, resource depletion and thermodynamic constraints limit operational continuity. Over the durations relevant for galactic travel, AI systems experience degradation in memory, hardware, energy, and software. Environmental unpredictability and cumulative errors increase operational risk. While AI may improve short-term mission performance, current data indicate that it cannot maintain system functionality or civilization-scale operations indefinitely across interstellar or intergalactic distances. The dark matter unknown. Even if a civilization could solve propulsion, closed ecological systems, and AI management, it would still confront one of the most profound obstacles in the universe: dark matter. This mysterious component constitutes approximately 85% of the total matter in the universe and dominates the mass of galaxies. Yet it interacts with ordinary matter primarily through gravity. For any civilization attempting to leave its galaxy, dark matter is an unavoidable environmental factor, introducing both navigational hazards and fundamental uncertainties that cannot be eliminated. The first challenge arises from the gravitational effects of dark matter. Unlike visible stars, gas, and dust, dark matter does not cluster in discrete, easily observable structures. Instead, it forms a diffuse halo surrounding galaxies, extending far beyond the visible stellar disk. In the Milky Way, this halo may extend up to 300,000 light-years, encompassing more mass than all the stars combined. For spacecraft attempting to leave the galaxy, the gravitational pull of this halo is significant. Trajectories calculated based solely on visible matter would underestimate the force required to escape, potentially leaving ships in unintended orbits, slowing their progress, or even pulling them back toward the galactic center. This gravitational influence is not uniform. Dark matter is distributed unevenly, with denser clumps forming within the halo. Simulations based on the Lambda Cold Dark Matter (LCDM) model suggest that there are thousands of subhalos, each containing masses ranging from millions to billions of solar masses. A spacecraft passing near one of these subhalos could experience sudden gravitational perturbations, altering its course in unpredictable ways. Over intergalactic distances, even minor deviations compound, making long-term trajectory prediction extremely difficult. Unlike a spacecraft within a galaxy, where stars provide navigational reference points, intergalactic travelers cannot easily detect or avoid these invisible structures. Our lack of understanding of dark matter properties compounds the problem. Despite decades of experimental efforts, including the Xenon 1T and Lux Zeppelin experiments, no definitive detection of dark matter particles has been confirmed. Scientists know it interacts gravitationally, but whether it has weak or other exotic interactions with normal matter remains unknown. This uncertainty makes it impossible to design spacecraft that can safely interact with, deflect, or shield against dark matter concentrations. Any unknown interaction, even at minuscule probabilities, could lead to catastrophic collisions at the speeds required for intergalactic travel. The problem of trajectory calculation is exacerbated by the dynamic behavior of dark matter. Halos are not static. They respond to galaxy mergers, tidal interactions, and internal dynamics. Studies of galaxy simulations, such as the Illustris TNG project, show that halo substructure can shift over millions of years, with dense clumps moving several thousand light-years relative to the galactic center. A spacecraft plotting a course for intergalactic escape would face a constantly shifting gravitational landscape, requiring continuous recalibration that becomes impossible over the timescales involved. Unlike within a galaxy, there are no easily observable reference points to correct for drift caused by these invisible forces. The presence of dark matter also affects potential propulsion strategies. Hypothetical concepts like beamed energy propulsion, fusion sails, or antimatter drives assume relatively predictable gravitational conditions. Navigating through dense dark matter regions could require sudden trajectory adjustments, consuming additional energy and potentially exceeding the power reserves of even the most advanced systems. The vast mass of dark matter implies that any significant maneuver requires large-scale energy expenditure, which is further compounded by the timescale over which intergalactic travel occurs. Over millions of years, these incremental corrections could deplete a spacecraft's resources entirely. Another consequence is the effect on long-term orbital stability. Dark matter halos exert tidal forces on spacecraft trajectories. These forces are weak over short distances but accumulate over galactic and intergalactic scales. Over thousands of light-years, small perturbations can slowly alter the path of a ship, increasing the risk of collision with sparse interstellar gas clouds or dark subhalos. Unlike conventional stellar navigation, where orbits are predictable, dark matter introduces a chaotic element that cannot be corrected without continuous observation and enormous energy expenditure. Even if civilizations developed highly advanced sensors capable of mapping dark matter in real time, the resolution required for effective navigation is staggering. Detecting subhalos of a few million solar masses over hundreds of thousands of light-years requires sensitivity orders of magnitude beyond current instruments like the Gaia Observatory, which measures stellar positions and motions to micro-arc-second precision. Extrapolating this technology to map invisible mass distributions over galactic scales pushes well beyond any plausible engineering scenario, particularly when factoring in resource limitations over cosmic timescales. The unknown composition of dark matter also poses theoretical hazards. If it includes weakly interacting massive particles, or WIMPs, axions, or other exotic forms, the interaction rate may be low but non-zero. A spacecraft traveling at significant fractions of light speed could, over millions of years, experience cumulative interactions that erode material integrity, alter electronics, or disrupt internal systems. While individually rare, the integrated effect over intergalactic distances could be severe. Any design relying solely on conventional shielding fails to account for these unknown risks. In addition, dark matter halos influence galactic escape indirectly by affecting stellar dynamics. Stars near the edges of the Milky Way orbit more slowly than previously thought due to the gravitational influence of the halo, as observed by surveys like SDSS and Gaia DR3. Predicting the precise orbital motion of stars for gravitational slingshot maneuvers becomes unreliable, complicating any attempt to leverage stellar gravity for acceleration or course correction. Unlike in interplanetary missions, where gravity assists are predictable, intergalactic journeys confront a highly uncertain and dynamic gravitational environment. The combination of unknown particle physics, diffuse mass distribution, and dynamic behavior creates significant navigational and energy challenges for spacecraft attempting galactic escape. Unlike cosmic radiation or micrometeoroids, which can be partially mitigated with shielding, dark matter interacts primarily through gravity and cannot be directly manipulated. Accounting for its effects requires continuous trajectory adjustments, energy expenditure, and precise navigation beyond current technological capabilities. Minor miscalculations in trajectory, compounded over millions of years, can result in spacecraft missing target galaxies. Unlike travel within a visible stellar environment, there are few observable markers to correct deviations caused by gravitational effects of dark matter, which is largely invisible and dynamically shifting. The dark matter halo of a galaxy affects trajectories, requiring additional energy for course corrections over long distances. Gravitational interactions with this diffuse mass impose constraints on spacecraft navigation that cannot be removed, and trajectory planning must account for its distribution and dynamic behavior. Dark matter significantly affects the gravitational contours of galaxies and complicates long-duration navigation, adding to challenges in propulsion, ecosystem management, and AI operation. Accounting for its effects requires adjustments in trajectory planning, energy management, and mission design for intergalactic travel, galactic collisions, and structural instability. Even if a civilization could navigate the dark matter halo, manage long-term ecosystems, and rely on sophisticated AI, it would face another cosmic obstacle: the dynamic instability of galaxies themselves. Galaxies are not static, serene islands in space. They are gravitationally bound systems of stars, gas, dust, and dark matter that continuously interact with their environment. Collisions, mergers, and structural evolution occur on timescales ranging from millions to billions of years, creating hazards that no civilization can fully anticipate or escape. The Milky Way, our home galaxy, provides a clear example of this instability. Observations from the Sloan Digital Sky Survey and Gaia mission indicate that the Milky Way is currently on a collision course with the Andromeda Galaxy. Although the projected encounter is not expected for approximately 4.5 billion years, simulations reveal the profound disruptions such events can produce. Stars are unlikely to collide directly due to vast interstellar distances, but gravitational perturbations will radically alter orbital paths, sending stellar populations into chaotic trajectories. Any spacecraft attempting galactic exit during such events would encounter dramatically changing gravitational landscapes, making navigation nearly impossible. Smaller scale mergers are even more frequent. Galaxies like the Milky Way regularly absorb dwarf galaxies. The Sagittarius Dwarf Elliptical Galaxy is currently being assimilated, stretching over tens of thousands of light years and producing streams of stars, gas, and dark matter. These mergers induce tidal forces that ripple through the galactic disk, displacing stars and gas clouds. Over millions of years, these effects continuously reshape the gravitational contours of the galaxy, complicating any long-term planning for escape routes or stable trajectories. A civilization attempting intergalactic travel cannot rely on static orbital calculations because the galactic environment is constantly shifting. Star formation bursts and radiation spikes accompany these structural instabilities. When galaxies collide or interact, gas clouds compress, triggering new generations of massive stars. Massive stars, in turn, end their lives in supernovae, releasing energy equivalent to billions of suns. Gamma-ray bursts may occur, threatening biological and artificial systems with lethal radiation across thousands of light years. Even civilizations hidden deep within galactic disks are not immune to these bursts, and any starship navigating the outer halo could find itself exposed to energetic events it cannot predict or avoid. Gravitational resonances further complicate matters. Stars within the galactic disk orbit the center at varying speeds depending on radius, creating patterns known as spiral density waves. These waves are not permanent structures. They shift over time due to the gravitational influence of nearby masses, including dark matter, subhalos, globular clusters, and passing dwarf galaxies. Navigating these dynamic regions requires constantly recalculating trajectories to avoid unintended acceleration, collisions, or gravitational trapping. For intergalactic journeys spanning millions of years, the cumulative effect of even small miscalculations could divert a spacecraft entirely off course. The instability is compounded by the presence of supermassive black holes at galactic centers. The Milky Way's central black hole, Sagittarius A star, contains approximately 4.3 million solar masses. Interactions with other massive objects during galactic mergers can perturb the black hole's gravitational influence, sending stars and gas into altered orbits. Even trajectories calculated to avoid the central region may encounter unpredictable gravitational shifts due to these effects. Unlike static obstacles, black hole perturbations emerge without warning, creating regions of heightened risk for any spacecraft. Galactic collisions are not isolated events. The local group, which contains more than 50 galaxies, including the Milky Way and Andromeda, experiences continuous minor interactions. These encounters produce tidal streams, warps in galactic disks, and oscillations in the distribution of stars and gas. Observations of the M81 and M82 system, for example, reveal how galaxies passing near each other can trigger bursts of star formation, strip gas, and eject stellar material into intergalactic space. A civilization attempting intergalactic travel must contend not only with major collisions but also with these ongoing minor perturbations that constantly reshape escape pathways. Even absent direct collisions, internal dynamics introduce long-term instability. Galactic bars' elongated central regions, present in many spiral galaxies, including the Milky Way, rotate and evolve over hundreds of millions of years. Bars funnel gas toward the central bulge, alter star orbits, and produce resonances that propagate throughout the disk. A spacecraft charting a course through these regions would find its intended gravitational assists, navigational beacons, and relative stellar positions changing unpredictably. Minor errors in trajectory calculations can magnify over millions of years, leading to catastrophic deviation from intended paths. Another risk arises from galactic rotation and shear. Stars in the Milky Way's disk orbit at roughly 220 kilometers per second. but orbital speeds vary with distance from the center. This differential rotation stretches and twists stellar neighborhoods over millions of years, separating initially proximate stars by thousands of light years. Any interstellar infrastructure, navigational network, or fleet attempting coordinated movement would struggle to maintain cohesion. Ships relying on reference stars for orientation would face a constantly shifting frame, gradually losing synchronization with origin civilizations or sister spacecraft. Structural instabilities also threaten resource availability. Gas clouds can be stripped or heated during mergers, reducing the amount of material available for starship, fuel, or life support production. Dense regions of star formation may temporarily enrich the interstellar medium with heavy elements, but this occurs unevenly and unpredictably. Over the millions of years required to reach intergalactic space, civilizations cannot rely on consistent resource distribution within their home galaxy. Galaxies are dynamic systems, evolving on timescales shorter than those required for intergalactic travel. Trajectories, energy budgets, and technological systems must account for the continuously changing gravitational and environmental landscape. Even with advanced propulsion, AI, closed ecosystems, and dark matter navigation, spacecraft must adapt to structural instabilities that alter trajectories over time. Galactic collisions introduce timing considerations. Periods of relative calm with minimal mergers, starburst events, or tidal perturbations are limited in duration. Spacecraft missions must account for these dynamic conditions in planning intergalactic trajectories. Predictive models must include interactions among dark matter, minor mergers, and supermassive black hole dynamics. Observational data suggests that galaxy mergers are common. Surveys using the Hubble Space Telescope have documented tidal tails, disrupted disks, and merging systems across billions of light years. Galaxies like the Milky Way continuously experience gravitational interactions that affect trajectories, star formation, and gas distribution. Spacecraft planning intergalactic travel must consider these dynamic conditions alongside other hazards such as dark matter and radiation. Galaxies experience continuous internal dynamics, collisions, tidal effects, and evolving structures. Interstellar and intergalactic missions must account for shifting gravitational and environmental conditions. Propulsion, AI, and life support systems must adapt to these evolving factors to maintain trajectories and mission objectives over long timescales. The technological plateau problem. Even if a civilization could survive the galactic instability, dark matter, AI limitations, and radiation hazards, another obstacle remains: the natural ceiling of technological progress. History demonstrates that breakthroughs accelerate and plateau in cycles, and physical laws impose absolute limits that no amount of ingenuity can surpass. Escaping a galaxy is not merely a question of ambition or resources. It demands sustained technological growth on scales and durations that appear impossible when measured against both historical trends and cosmic realities. Human history offers a sobering perspective. In the past 500 years, humanity has witnessed dramatic leaps. The telescope, steam engines, electricity, nuclear energy, and computers. Yet over the last few decades, certain metrics suggest a slowdown in foundational breakthroughs. Research by scholars such as Robert Gordon indicates that the rapid growth seen in the late 19th and early 20th centuries may have been exceptional. Moore's law, the doubling of transistor density roughly every 2 years, now faces physical constraints as quantum effects disrupt semiconductor behavior at nanometer scales. Even if alternative computing paradigms, quantum, optical, or neuromorphic systems emerge, their performance gains are unlikely to scale indefinitely. On intergalactic timescales, civilizations face long periods in which technology simply cannot improve fast enough to overcome cosmic challenges. Material science illustrates another ceiling. Propulsion systems capable of approaching significant fractions of light speed demand materials that can withstand extreme acceleration, high-energy particle flux, and temperature variations across millions of years. Current high-performance alloys and composites, titanium aluminides, carbon-carbon composites, graphene derivatives offer impressive strength-to-weight ratios, but all have finite limits. Radiation, cosmic dust impacts, and micrometeoroid bombardment gradually degrade surfaces. Exotic concepts like metallic hydrogen, space-time manipulations, or hypothetical ultra-dense metamaterials remain unproven. Even assuming perfect design and fabrication, these materials confront limits dictated by atomic bonding, thermodynamics, and relativistic mechanics. Civilization-scale engineering cannot create matter stronger than the fundamental forces allow, meaning that propulsion, shielding, and structural support all face insurmountable ceilings. Energy availability further constrains technological escalation. Our Sun emits roughly 3.8 times 10^26 watts, yet interstellar travel requires harnessing energy orders of magnitude beyond what a planetary civilization can deliver. Dyson's theoretical megastructures, a shell or swarm capturing most of a star's output, remain hypothetical and would take millennia to construct. Even if implemented, the energy budget for accelerating a spacecraft to a significant fraction of light speed, compensating for galactic gravitational forces, and maintaining life support or AI systems is astronomical. Civilization must continually innovate in energy capture, storage, and conversion. But physical limits of stellar luminosity, conversion, efficiency, and thermodynamic loss impose a plateau beyond which energy acquisition cannot scale. Computation faces similar ceilings. Spacefaring civilizations may rely on massive onboard AI to handle navigation, life support, and self-repair over millions of years. But computation itself is bounded by physics. Landauer's principle, relating the minimum energy required to erase a bit of information, sets a hard limit on energy efficiency. Even advanced photonic or quantum processors cannot circumvent these fundamental constraints indefinitely. Furthermore, radiation exposure, thermal management, and material fatigue restrict how much computational density can be safely deployed. A civilization cannot infinitely increase processing power to compensate for other limitations without eventually encountering physical ceilings. Propulsion technology is constrained in comparable ways. Chemical rockets, nuclear thermal systems, antimatter drives, and theoretical beamed propulsion each face severe limitations. Chemical rockets have exhaust velocities too low to make intergalactic travel feasible within practical timescales. Nuclear propulsion provides higher energy density, but is still insufficient to reach even 10% of light speed for massive vessels. Antimatter offers immense energy per unit mass, but requires storage technologies that do not yet exist and may never be stable over millennia. Beamed propulsion relies on constructing energy emitters on scales equivalent to planetary surfaces. Across all options, technological innovation can improve efficiency, but cannot escape the absolute energy and material constraints imposed by physics, which define a plateau beyond which further progress yields diminishing returns. Even hypothetical exotic concepts, often popularized in speculative physics, illustrate the problem. Warp drives, wormholes, and space-time manipulations require negative energy densities or exotic matter, none of which have been demonstrated experimentally. Theoretical models often assume idealized conditions, ignoring practical engineering, energy acquisition, and stability. Calculations indicate that constructing even a minimal warp bubble capable of transporting a spacecraft would require mass energy comparable to that of a star or more, orders of magnitude beyond the production capabilities of any plausible civilization. In other words, even if the underlying physics permits certain extreme technologies, practical limitations on construction, energy, and maintenance impose an effective plateau. Historical megastructure proposals illustrate these constraints concretely. Concepts such as O'Neill cylinders, Stanford Torrey, and massive interstellar arcs highlight the scale required to sustain life over millennia. Each requires resource mobilization on a planetary or stellar scale. A Dyson swarm capturing a significant fraction of solar output would demand mining and construction operations, consuming entire planetary masses over centuries. Scaling such projects to the level required for intergalactic travel amplifies the problem exponentially. The technological and economic commitment is staggering, and any failure in planning, materials, or execution could doom the entire enterprise. Technological limitations interact with other cosmic hazards. Stellar collisions, supernovae, galactic mergers, and dark matter perturbations create dynamic conditions that require continuous adaptation. Each measure consumes energy, materials, and computational resources, constrained by the absolute tolerances of physical systems and engineering limits. Technological progression over long timescales is affected by social and organizational factors. Sustaining complex projects across thousands or millions of years depends on maintaining coordination, resource allocation, and operational continuity. Interruptions, misaligned priorities, or resource scarcity may constrain long-term technological development in addition to physical and material limits. Physical, material, and energy limitations define a ceiling for technological development. Scaling challenges, dynamic cosmic hazards, and the requirements of long-term projects constrain energy, computation, materials, and propulsion capabilities. Over centuries or millennia, these factors limit the potential for intergalactic travel, requiring careful planning to operate within the bounds of known physics and engineering constraints. The logistics of no return. Even though a civilization could overcome the technological plateau, navigate galactic instability, and manage energy, propulsion, and AI systems, it would still confront a profound logistical reality. Leaving a galaxy is inherently a one-way journey. Unlike interplanetary missions, where supply lines, orbital assets, and distant colonies can support crew and infrastructure, intergalactic travel offers no possibility of resupply or rescue. Every system, every resource, and every contingency must be planned for decades, centuries, or even millions of years in advance, with zero margin for error. Current human space missions highlight the severity of this challenge. The International Space Station, orbiting just 400 kilometers above Earth, relies on regular deliveries from cargo vehicles such as SpaceX's Dragon, Northrop Grumman's Cygnus, and previously the Russian Progress. Even in this near-Earth environment, delays, miscalculations, or accidents can lead to resource shortages or mission failure. Extending these principles to interstellar distances demonstrates the scale of the problem. Voyager 1, launched in 1977, is now over 23 billion kilometers from Earth, yet it carries no means to resupply or repair itself. Its power, fuel, and instrumentation are finite, and its longevity is measured in decades, not millions of years. Extrapolate this to intergalactic travel, where the nearest galaxy, Andromeda, lies approximately 2.5 million light-years away. Even travelling at 10% of the speed of light, a velocity far beyond current human capabilities, it would take 25 million years to arrive. During such durations, any civilization must ensure that life support systems, propulsion mechanisms, and communication infrastructure function without interruption, degradation, or failure. Unlike interstellar missions within a galaxy, there is no possibility of docking with waypoints, receiving supply drops, or leveraging natural resources along the route. Every kilogram of fuel, raw material, and structural component must be carried from the outset, and redundancy becomes both critical and exponentially burdensome. The logistics of provisioning amplify exponentially with mission scale. A single vessel carrying human passengers requires consumables such as water, food, oxygen, and radiation shielding. Even closed-loop systems, like NASA's Biosphere 2 experiments, encounter microbial instability, nutrient cycling failure, and cumulative biological drift over decades. Scaling such a system to support hundreds or thousands of individuals over millions of years would require resource reserves orders of magnitude beyond the total biomass of a planet. Any minor miscalculation, such as the growth of an unforeseen microbial species or the depletion of trace elements, could trigger cascading failures with no opportunity to correct externally. Fuel logistics present an equally daunting problem. High-energy propulsion concepts, including nuclear thermal rockets, fusion drives, or beamed propulsion, require fuel-mass ratios that increase exponentially with intended speed and distance. Even assuming perfect efficiency, the sheer quantity of matter needed for continuous acceleration over millions of years far exceeds the mass of most planetary systems. Civilizations attempting intergalactic travel cannot rely on en route harvesting, because intergalactic space is largely empty, with matter densities below 1 atom per cubic centimeter. Once the initial fuel is expended, there is no chance of replenishment, making planning errors fatal. Maintenance and repair further complicate logistics. Even self-replicating robotic systems encounter wear, cosmic radiation damage, and material fatigue over extended durations. Voyager probes, for instance, have seen system degradation despite being protected by Earth-based monitoring and occasional software updates. In intergalactic missions, ships cannot rely on outside assistance. Autonomous repair systems would need to function indefinitely, without resupply or recalibration, against cumulative micrometeoroid impacts, high-energy particle bombardment, and unpredictable material failure. The probability of system failure, even with high redundancy, approaches certainty over millions of years. Communication presents another unmanageable constraint. Signals across intergalactic distances experience delays of millions of years, rendering coordination with a home civilization effectively impossible. Even if an advanced civilization maintains transmission power sufficient to reach the other side of a galaxy, synchronization with origin infrastructure would be lost. Commands, updates, and emergency corrections cannot be received in a meaningful time frame. Any mission must be entirely self-contained, with decision-making delegated to onboard AI or crew, who themselves are limited by finite knowledge of conditions beyond the galaxy. There is no external guidance or rescue in emergencies, making the endeavor inherently one-way. The psychological and societal logistics of one-way intergalactic travel are equally severe. Civilizations attempting such journeys would need to maintain cultural continuity, social cohesion, and technical expertise across millions of years. Linguistic drift, memory degradation, and evolving priorities could render the original mission objectives unintelligible or irrelevant to future generations. Even if a spacecraft carries advanced AI to preserve knowledge, these systems face hardware degradation, cosmic radiation, and entropy that ultimately erode reliability. Unlike shorter duration interstellar missions, intergalactic expeditions cannot rely on returning to reinforce or correct social, cultural, or operational frameworks. Redundancy is constrained by mass and complexity. Carrying multiple backup systems for propulsion, life support, energy, and AI increases fuel requirements. Each additional layer of redundancy requires careful calculation, but risks of system failure accumulate over long durations. Intergalactic travel logistics require planning across multiple interdependent variables over extended timescales. Historical megastructure concepts illustrate the logistical scale of intergalactic travel. Freeman Dyson proposed capturing the energy of a star to support large projects, while Gerard O'Neill envisioned rotating habitats for long-term habitation. Scaling these concepts for intergalactic travel increases requirements for energy capture, material acquisition, and system maintenance across geological timescales, with additional constraints from entropy, cosmic hazards, and unpredictable events. One-way intergalactic missions require complete self-sufficiency. A civilization cannot rely on resupply or external assistance during the journey. Fuel shortages, equipment failure, or unforeseen cosmic events must be accounted for in initial planning and redundancy. Intergalactic travel imposes strict logistical constraints with no possibility of mid-course correction. Intergalactic travel logistics combine constraints from propulsion, materials, energy, biological systems, mechanical reliability, and social factors. Cosmic hazards, including radiation, dark matter, and galactic instability, impose additional challenges. Planning must ensure that all systems function autonomously over millions of years, with no opportunity for external correction, resupply, or adaptation. False hope in hypothetical physics. After confronting the logistics of no return, civilizations might be tempted to look for loopholes in the laws of physics. For millennia, humanity has been drawn to the allure of shortcuts, warp drives, wormholes, and exotic matter constructs that promise faster-than-light travel. These ideas often dominate science fiction, yet careful scientific scrutiny reveals why they remain firmly speculative, and why, even if possible in principle, they cannot scale to the intergalactic level. No matter how imaginative the engineering, the universe enforces strict rules that prevent civilizations from bypassing the barriers that cosmic distances impose. The concept of the warp drive has fascinated physicists and engineers since Miguel Alcubierre proposed a mathematical model in 1994. In theory, a warp bubble could contract space in front of a spacecraft and expand it behind, allowing the vessel to traverse vast distances without locally exceeding the speed of light. At first glance, this seems to offer an elegant solution to intergalactic travel. Move faster than light without breaking relativity. However, practical calculations reveal severe limitations. A 100-meter ship traveling at modest warp parameters might require the mass energy equivalent of Jupiter in negative energy densities. Even small increases in velocity scale energy requirements astronomically, making the concept currently impossible to implement. Moreover, the hypothetical exotic matter required to stabilize a warp bubble has never been observed in nature, and producing sufficient quantities could demand resources exceeding the mass of entire stars. Wormholes present another tempting shortcut. In principle, a traversable wormhole could connect two distant points in space-time, allowing instantaneous travel across millions of light years. Theoretical models, such as those explored by Kip Thorne and colleagues, suggest that maintaining such a wormhole would require matter with negative energy density to prevent collapse. Yet no experiment has ever detected stable negative energy in usable amounts. Even if it existed, the energy cost of holding a wormhole open, counteracting tidal forces, and preventing collapse would be immense. Calculations indicate that stabilizing a wormhole capable of carrying a spacecraft would likely demand more energy than the output of several stars over millions of years. The practical impossibility is compounded by the unknown interactions of wormholes with radiation, matter, and dark energy factors that could destroy or destabilize the structure long before a ship passes through. The idea of using Casimir effects or vacuum fluctuations to manipulate space-time has also been explored. Physicists like Matt Visser have proposed that quantum field effects could, in theory, create regions of negative energy density. But the magnitudes involved are vanishingly small orders of magnitude below what would be required for a macroscopic warp or traversable conduit. While laboratory experiments can measure Casimir forces between tiny metal plates, scaling these effects to create a stable structure capable of carrying a starship is far beyond any realistic engineering capability. The gap between theoretical possibility and practical implementation remains insurmountable. Even beyond energy and material challenges, hypothetical physics encounters temporal obstacles. Intergalactic travel requires systems that remain operational for millions of years. Warp drives, wormholes, or any exotic space-time manipulation would be subject to cumulative effects from cosmic rays, micrometeoroid impacts, and quantum fluctuations. Unlike conventional propulsion or structural engineering, these systems have no precedent for long-term stability. Any disruption in the exotic matter field or collapse of a space-time bubble could annihilate the ship or strand it indefinitely. The very phenomena that make such shortcuts theoretically attractive also make them highly fragile in the real universe. Speculative concepts often overlook scaling limitations. While some exotic physics proposals might work over laboratory scales or perhaps planetary distances, intergalactic distances are so vast that energy requirements, material stress, and system redundancy grow faster than any conceivable civilization could manage. Even a star-spanning civilization harvesting the output of billions of stars would struggle to generate the required energy densities for sustained warp propulsion or wormhole stabilization. These ideas remain fundamentally incompatible with the timescales and scales involved in leaving a galaxy. Historical context also illustrates the allure and danger of false hope. Throughout history, civilizations have repeatedly pursued ideas that seemed theoretically possible but proved impractical when scaled. The medieval dream of perpetual motion machines and alchemical transmutations captivated engineers and scholars for centuries. Even in the modern era, concepts like cold fusion and room temperature superconductors have sparked intense research, only to demonstrate the limits imposed by fundamental physics. Hypothetical, faster-than-light travel is analogous on a cosmic scale, mathematically conceivable under certain assumptions, but practically unattainable given the energy, material, and temporal constraints. Not all speculative physics is purely destructive. Certain ideas, such as beamed propulsion using lasers or solar sails, operate within known physics and have been tested on small scales. Projects like Breakthrough Starshot aim to accelerate gram-scale probes to 20% of light speed using focused laser arrays. Yet even these realistic approaches face insurmountable barriers when scaled to intergalactic travel. The mass of a crewed starship, shielding, and life support increases requirements by many orders of magnitude, rendering energy and materials demands effectively infinite. In this context, the contrast between speculative and realistic solutions is stark. Hypothetical shortcuts remain enticing, but ultimately irrelevant. Another dimension is the unpredictability of cosmic hazards. Exotic physics cannot insulate a ship from gamma-ray bursts, supernovae, interstellar dust at relativistic velocities, or the unpredictable gravitational shifts caused by dark matter substructures. Even if a warp bubble could theoretically move a ship faster than light, it would still need to survive the same fundamental environmental hazards that plague conventional starships. Faster travel does not eliminate radiation, navigation errors, or system failures. It only compresses the timescale, concentrating risks rather than mitigating them. Engineering hypothetical faster-than-light systems must account for entropy, cosmic hazards, finite energy, and material limitations. Mathematical models of negative energy, stable wormholes, or warp bubbles describe idealized scenarios, but practical implementation faces extreme energy, stability, and scalability challenges. Intergalactic distances impose constraints that cannot be ignored in planning or design. Warp drives, wormholes, and exotic matter constructs have energy, stability, and scaling requirements that exceed any currently conceivable engineering capability for intergalactic travel. Systems would need to operate reliably over millions of years while withstanding cosmic radiation, micrometeoroid impacts, and gravitational perturbations. These constraints make hypothetical faster-than-light methods impractical for covering intergalactic distances. Why no evidence of galactic migrators exists? If civilizations could overcome technological limits, logistics, and even hypothetical physics, one might expect traces of such attempts to be observable in the cosmos. Intergalactic migration, after all, would leave detectable signatures, massive energy usage, displaced stars, or artificial megastructures visible from millions of light years away. Yet astronomical surveys reveal no evidence of civilizations leaving their galaxies, and the silence itself tells a compelling story about the practical impossibility of intergalactic escape. Human observation of the cosmos has advanced rapidly over the last century. Optical, infrared, and radio telescopes have surveyed millions of galaxies. The Sloan Digital Sky Survey has catalogued over 930,000 galaxies in the local universe, while infrared observatories like the Spitzer Space Telescope and Wide Field Infrared Survey Explorer, or WISE, have measured heat emissions across entire galaxies. Scientists expected that any civilization undertaking large-scale intergalactic projects, such as building energy-collecting megastructures or launching fleets of massive spacecraft, would produce detectable waste heat or anomalies in these surveys. Yet the data show no deviations from natural stellar or galactic activity beyond statistical noise. One proposed signature of galactic migration is the presence of Dyson spheres or swarms around a substantial fraction of a galaxy's stars. Freeman Dyson suggested that an advanced civilization might capture the bulk of a star's energy for propulsion, computation, or colonization. A galaxy populated with such megastructures would exhibit abnormal infrared output. The stars would appear dimmer in visible light, but emit excess heat detectable in mid to far infrared wavelengths. Yet, WISE and other surveys have found no galaxies displaying such systematic anomalies. Out of hundreds of thousands examined, only a handful of galaxies show minor irregularities, none of which correspond to the scale required for intergalactic migration. Radio astronomy offers another perspective. The Breakthrough Listen initiative and similar projects scan millions of stars for narrow bandwidth signals indicative of intelligent activity. Even if only a small fraction of civilizations attempted intergalactic travel, detectable radio signatures could appear over millions of years. However, the observations reveal no sustained, coherent transmissions that would suggest large-scale coordination or communication over intergalactic distances. Any signals from spacecraft or home civilizations would be diluted across millions of light years, falling below detection thresholds, reinforcing the notion that practical migration remains impossible. Some scientists have searched for physical evidence of interstellar probes at local scales. The concept of von Neumann probes, self-replicating spacecraft, assumes that any civilization capable of leaving its galaxy could, in principle, send autonomous machines to explore or prepare distant regions. Such probes might leave observable artifacts in asteroid belts, stellar systems, or intergalactic space itself. Yet despite decades of exploration, including detailed surveys of the Kuiper Belt, Oort cloud, and nearby star systems, no anomalous objects of artificial origin have been confirmed. Even the detection of interstellar objects like Oumuamua and 2I, Borisov, which traverse the solar system, has not revealed any artificial design. Their trajectories, composition, and behavior remain consistent with natural objects. Energy requirements for intergalactic propulsion exceed the output of billions of stars, and maintaining life support, or AI, over millions of years presents extreme engineering challenges. Based on these constraints, detectable artifacts from intergalactic migration are unlikely to exist. Galaxy-scale surveys show no signs of structural disruption consistent with mass migration. Galaxies are dynamical systems. Star clusters, spiral arms, and gas distributions evolve under precise gravitational balances. Removing significant stellar mass or redistributing matter on interstellar scales would produce observable anomalies. Observations of the Milky Way, Andromeda, and nearby galaxies are consistent with natural evolution, stellar formation, and tidal interactions. Infrared data also rules out the idea of energy-intensive propulsion projects. Hypothetical propulsion on a galactic scale would release massive waste heat, either from antimatter annihilation, fusion drives, or hypothetical space-time manipulation. For example, accelerating a starship to a fraction of light speed using fusion-based propulsion would emit energy comparable to that of a medium-sized star, yet surveys have not identified any galaxy exhibiting systematic thermal anomalies. Even the most optimistic estimates of civilization density suggest that if intergalactic migration were feasible, detectable heat signatures would have accumulated over millions of years, and we would have observed them by now. Historical assumptions in science fiction offer context for the discrepancy between expectation and observation. Early writers such as Isaac Asimov and Arthur C. Clarke often imagined galaxies filled with migrating civilizations or fleets of generational starships. These narratives assumed both near-infinite technological scalability and negligible cosmic hazards. Modern astronomy and physics demonstrate that these assumptions are inconsistent with reality. The absence of intergalactic artifacts is not merely a gap in observation, it reflects fundamental constraints on energy, materials, time, and system reliability. The universe is simply too vast, and the practical barriers too severe for any civilization to leave its galaxy in detectable numbers. Observations do not detect evidence of civilizations traveling between galaxies. The combination of technological, logistical, energy, and physical constraints makes intergalactic migration extremely unlikely. Cosmic distances, material limits, and long timescales present additional challenges to such endeavours. Observations do not detect evidence of civilizations leaving their galaxies. Energy limitations, material constraints, system degradation, and relativistic travel requirements make intergalactic migration highly challenging. Astronomical surveys, infrared data, and radio observations have not identified footprints, heat signatures, or mass anomalies that would indicate such activity. Galaxies as ultimate cosmic islands. By the time we reach the final stretch of this exploration, the evidence from physics, logistics, energy constraints, radiation hazards, and observational astronomy converges on a stark reality. Galaxies are natural cosmic islands, and no civilization can ever cross the vast voids that separate them. The Milky Way, the Andromeda Galaxy, and the countless other galaxies populating the observable universe are each effectively isolated by the unyielding laws of nature. Understanding why requires a synthesis of galactic structure, evolution, and the interplay of physical constraints on life, technology, and travel. Galaxies are immense systems of stars, gas, dust, dark matter, and gravitationally bound planets. The Milky Way, for example, spans roughly 100,000 light-years in diameter and contains over 200 billion stars, yet the average distance between stars is on the order of 4 light-years. Beyond the visible stars, galaxies are embedded in halos of dark matter which dominate their total mass. The Milky Way's dark matter halo extends for more than 300,000 light-years and contributes roughly 85% of the galaxy's mass. Any trajectory leaving a galaxy must account for gravitational influences from both visible and unseen matter, which can subtly alter paths over millions of years. The intergalactic medium presents another challenge. Between galaxies lies a near-perfect vacuum, with particle densities often less than 1 atom per cubic centimetre. Temperatures can approach 10 million Kelvin in galaxy clusters, and the environment is dominated by highly energetic cosmic rays and occasional gamma-ray bursts from stellar collisions or supernovae. Any spacecraft travelling between galaxies must carry all necessary shielding, fuel, life support, and maintenance capabilities, because there is no opportunity to harvest matter en route. These conditions require resource allocations far beyond those needed for planetary or galactic travel. The expansion of the universe adds additional constraints. Galaxies are not static. The universe is expanding at approximately 73 kilometers per second per megaparsec. While gravitationally bound galaxies like the Milky Way and Andromeda remain in the local group, most other galaxies recede at velocities exceeding the speed of light relative to us due to cosmic expansion. Even with relativistic travel, many galaxies in the observable universe would move beyond the distance light can traverse. Life and civilization arise under local environmental conditions. Planetary chemistry, stellar radiation, and planetary dynamics all influence biological development. Galaxies can be considered isolated environments due to the distances between them. Intergalactic distances are far larger than any known biosphere or planetary system, presenting significant gravitational and logistical challenges for expansion. Observational astronomy provides data on the distribution of galaxies. Surveys using instruments such as the Hubble Space Telescope, Chandra X-ray Observatory, and WISE have not detected intergalactic artifacts, megastructures, or anomalous energy distributions. Infrared studies could detect excess waste heat if civilizations moved significant mass or constructed energy-intensive propulsion systems. No anomalies of sufficient scale have been observed. A spacecraft leaving the Milky Way at 10% the speed of light would require approximately 25 million years to reach Andromeda. the nearest large galaxy. During this time, navigation, life support, and structural integrity would need to operate continuously. Material fatigue, radiation damage, or system decay could terminate the mission, as no opportunities for resupply exist during intergalactic transit. Within a galaxy, star-to-star travel involves immense distances, energy limitations, and cumulative system failure risks. Civilizations could expand gradually within local stellar neighborhoods, spanning tens to hundreds of light years, but energy and logistical demands increase rapidly with distance. Expanding to another galaxy would multiply these challenges by factors of millions. Historical and theoretical trends indicate that physical and logistical limits constrain expansion, energy consumption, material production, and technology scale sublinearly with size and ambition. Extrapolating these trends to intergalactic distances shows that current or projected energy sources, propulsion technologies, and system architectures are insufficient to overcome the combined constraints of distance, time, and environmental hazards, even for advanced civilizations such as Kardashev Type 2 or early Type 3. Galaxies are spatially and physically distinct due to gravitational structure, the intergalactic vacuum, cosmic expansion, radiation hazards, energy constraints, and time. These factors limit the feasibility of intergalactic travel. Observational data show no evidence of civilizations moving between galaxies, consistent with physical constraints and logistical challenges. Interstellar exploration within a galaxy remains theoretically possible on long timescales, but intergalactic travel would require resources and technology far beyond current or projected capabilities. Each galaxy functions as a largely self-contained environment for life, energy use, and civilization activity. The intergalactic void presents extreme physical and logistical challenges. The universe provides a profound lesson. Cosmic ambition is bound by immutable laws. Galaxies, with their massive scales, gravitational complexity, and isolation enforced by intergalactic space, are ultimate islands. Civilizations, no matter how advanced, are confined to these domains, where energy, logistics, and time define the limits of expansion. Observations, physics, and theoretical modeling all converge on this conclusion, leaving no ambiguity. The dream of leaving one's galaxy remains forever beyond reach, and the vast islands of the universe continue to drift in quiet isolation, hosting civilizations that can grow only within their own cosmic harbors.